Hello, everyone, and welcome to the International Symposium on Alternatives Assessment. The theme of our symposium this year is Accelerating Safer and Sustainable Alternatives. We're just going to wait a minute or two while we see people are still joining us. This is the biggest symposium we've had to date, so we're very excited and energized. We have three great speakers today. They're all from the US EPA. Our short course, just to make sure you're in the right place, is tour de force of tools from the US Environmental Protection Agency to support assessments of alternatives. My name is Meg Whitaker. I'm program co-chair of A4, and I hope you enjoyed today's short course. Let me briefly introduce our speakers. I'll do it alphabetically. Todd Martin is a research chemist at the US EPA. Dr. Martin has been with the US EPA Office of Research and Development at the US EPA since 2002. He's a chemical engineer by training, and his research is focused on computational toxicology and alternatives assessment. Among other things, he's the lead developer of TEST. TEST, as many of you know, estimates toxicity values and physical properties from molecular structure. It's a great tool. I can buy for that. He's also the lead developer for the Hazard Comparison Dashboard, also known as the HCD. The HCD is a web tool that allows users to easily compare the hazards of chemical alternatives using chemical lists, experimental toxicity data, and predicted toxicity values. Then we have Catherine Phillips. She's a physical scientist from the US EPA. She's worked with the US EPA's Office of Research and Development since 2016. So I guess you're a newbie on the team. While her formal training was chemical engineering, Catherine now focuses on gathering data related to human exposures to chemicals and developing models which help fill gaps in where those data are missing. In collaboration with the EPA scientists, Catherine's developed models which predict a chemical's functional use in consumer products and databases containing publicly available information of uses and weight fractions of ingredients in consumer products, which are used to obtain high throughput exposure estimates. I'm looking forward to learning about that myself. And then finally, we have Anthony Williams. He's a computational chemist at the EPA. He joined the Center for Computational Toxicology and Exposure in the Office of Research and Development in May 2015. He's a chemoinformatician, I knew I was going to mess that up, focused on the delivery of the center's data to the scientific community via the Toxicomedicals dashboard. Anthony's interests include the aggregation and curation of chemical data, development of models to support physicochemical property prediction, and development of software approaches to support non-targeted analysis. He's got over 2 decades of experience in chemoinformatics and chemical information management with a focus on internet-based projects to deliver free access, community-based chemistry websites. That is music to my ears. Next slide, please. So here's our agenda for today. And we do have short breaks between each of these sessions. From 11 to 12, we're going to get introduction to the dashboard from Tony. There will be a 5-minute break. And then from 12:05 to 1:05 p.m., we're going to go into Qscr modeling approaches, and Todd's going to teach that. Then from 1:20 to 2:05, we're going to get into exposure data and models. Catherine's going to teach that portion. And then from 2:10 to 3 p.m., we'll discuss future plans. Next slide. So here's some short course etiquette. Please keep your lines muted and your videos off. Please make sure your full name and organization are noted. You can change your name by clicking on the little dots next to your name or image. Hopefully there'll be no names like Superpower Activator or something like that when we know who you are. If that happens, use speaker view in Zoom. It'll be the best viewing experience. And we do encourage questions. So if you do have a question, please raise your hand. And then during an appropriate stopping place, we'll turn to you and then we'll let you ask your question. Molly Jacobs is going to be in charge of this for us. So feel free to unmute your line and turn on your video to engage with us. I mean, this part of this is learning. Also, please feel free to use that chat, especially if you're just too shy. This session is being recorded and will be available next week on the A4 website. Next slide. And this is just how to raise your hand in Zoom. I'm pretty sure we're all fairly familiar with that now to do that. But again, the chat works too, if you, maybe you're on a slow connection, etc. Here are just two little quotes to think about before we get started. You can go to the next slide though. Here's a good quote I read about this morning. If you want to go quickly, go alone. If you want to go far, go together. And equally important, a stumble may prevent a fall. So all of these tools you're learning about today, especially if you haven't used them before, we're here to teach you about them because that's part of our mission of A4. And we're doing it together as a community so that we can all learn to advance safer and sustainable chemicals and materials throughout the supply chain. So let's dive right into it. Here's an introduction to the dashboard.
Good morning. So I'm Anthony Williams. I'm assuming if I could get a thumbs up or somebody comments that you can hear me okay.
Looks great and sounds great. Thank you.
Okay, great. So I have the position of kicking off the lead off, and I'm so happy to be doing this with two of my esteemed colleagues who I love working with. When you look at the dashboard, it's a little bit like drinking from a fire hose in some cases. There's so much to do. A deep dive, hands-on training, and we're going to try and do some of that today, is many, many hours, and there's always a little bit more to learn. So what you should understand is we're going to give this presentation to you with a certain flavor. This is intended for this audience. If we were talking to a group of mass spectrometry people, we would take a different spin on it. If we were talking to people who are interested in modeling, we'd go much deeper than Todd is going to do. But this is going to be an overview, and our email addresses are going to be scattered throughout our presentations on each of the lead slides. You will get it right at the end. And we encourage you to follow up with us with more questions after the session. So now you've seen who I am. I'm actually going to switch off the video so I can make sure that I have the best bandwidth for the presentation. And move back to sharing. I'm going to bookend the presentation right at the beginning and right at the end with this particular article that was published recently with a colleague from Europe, Jean-Louis Dawn, who's at EFSA, and also Jason Lambert and Chris Thayer, who are here at the EPA. And this might be one of the most pointed articles for your purposes. We publish a lot of articles on the dashboard, but this might be a very, very useful one for you to check out. If you can't get access to it, please let us know and we'll forward you a copy. So the problem, as we know, is there are a lot of chemicals that we...
Anthony, sorry for interruption, but the yep. View that we see is kind of like your speaker view with the showing of the next
flip
slide.
Again. Is that better?
Perfect. That works.
Okay.
Yep.
So the problem we have is that there are way too many chemicals coming into the marketplace. We also have, of course, the degradation of chemicals in the environment, transformation products, metabolites, et cetera, and there's so many chemicals that we need to turn our mind to. We certainly cannot characterize all of these efficiently. We cannot run long-term studies on all of these. So what we have to do is try and come up with ways to model these data, to pull the experimental data that is available together into a resource that people can access. Primarily for our own purposes initially, we were building this for our own needs. But of course, with the thrust towards access to data for everybody and being the EPA on the leading edge of access to computational toxicology data, we've tried to build resources that allow you all to have access. What you're going to hear about today is the newest tool in the armory, really, that pulls that data together. If you've been watching what the National Center for Computational Toxicology was doing, that's NCCT, you will have realized that we went through a reorg recently, and we are now the Center for Computational Toxicology and Exposure, and it's grown much, much bigger than it originally was. We're approaching 500 people now. So what you may be aware of from history is the ToxCast dashboard, the EDSP 21 dashboard, the CPCAT dashboard. These are all tools that were built originally, And what we've tried to do is pull all of these together into one application. And the intention is always to give you access to the data that we can pull together, the data that we measure, the data that we model. And because chemistry never stops, and there are always new chemicals that we need to be aware of and concern ourselves with, there's not always that much data available. So we will pull what we can and put it out. So this slide was written just 2-3 months ago. And at this point, SciFinder, most of you will know of Chemical Abstract Services, had 171 million chemicals in the registry. So I went on about 20 minutes to see how many are there right now, and I believe we've hit 189 million. That's how fast chemistry is growing in the Chemical Abstracts registry, 189 million. There are over 250 million unique CAS numbers. The estimate I have heard of is 50,000 new substances per day are being registered into the registry. We are not trying to compete. We're not trying to do the same job. We are trying to pull together data specifically related to environmental chemistry and chemicals of interest to our community. So the intention early on, right in the early days of the application, was to pull together chemistry data only. So chemical structures, numbers, names, maybe get us some of our modeled data in there, our experimental data used for modeling into this application. But with time, it became clear that what we were building could be of utility if we pulled all of the other applications that were already hosted within the center into one. And that's what we've done. We've switched off the older applications now. We've got one left over called Actor. Some of you may know that one. Actor ultimately will also be pulled into this dashboard. We were trying to build a first stop shop. It would be very arrogant for us to say we're the only game in town, because we're not. There's so many other good systems that are being built across the world, across the US government for sure. If you look at FDA, NIH, there's so many good systems coming online, but we wanted to provide a first stop shop for you to come and access the data. And this would be for the data relevant to environmental chemistry. And it would include exposure data, hazard data, dosimetry, that ToxCast, Tox21. Not only would we give you access to the experimental data that we pulled together, but we would give you access to the predictions that we have been able to build from those data over the years. And Todd is one of the experts in the field. So providing access to his pre-predicted data for every chemical that we register would be ideal. Catherine Phillips is a modeler. She also is going to talk about some of the models that she's built, and taking advantage of working with these incredible intellects that build these models. The application that I'm going to show you to start off with is giving access to their work. We want to make sure it's fully publicly accessible. You don't have to register. We don't need all of your details. It's just an open access website. The intention was always to update it regularly. And for the first 5 years that the application was online, we were doing releases every 6 months. We took a pause recently to do a full rebuild, because we started with a very, very basic vision of what this could be. Then over 5 years, we released 10 different versions every 6 months, pushing new data out to the community, adding the number of chemicals, generally between 10 and 20,000 chemicals every 6 months. And then also not just assembling data for the sake of, not just pulling chemicals together, but curating it, making sure that the data that we provide you is as high a quality as we can possibly assemble. We have 5 full-time curators that work only on the chemicals themselves. We have curators working on the hazard data. We have approaches to ensure that the bioactivity data is being fit, refit, analyzed, et cetera, et cetera. And providing access to these data is ultimately going to improve the efficiency that is necessary around chemical risk assessment, and ultimately, of course, accelerate the process. So a little bit about Chem Informatics, and depending on who you talk to, some might call it Chemo Informatics. I prefer it without the O personally. It's bringing together computer science and informatics and the knowledge and understanding of chemistry to try and pull together the knowledge that can come through associating chemical structures, substances, reactions, pull all of that data together, database it, wrap it in the appropriate delivery system so that we can give it out to the community. And some of you will be using things like PubChem, ChemSpider, Etiquette, Toolbox, etc., etc. A big part of this, of course, is modeling the data, so computational toxicology and exposure. So a lot of modeling goes on in our center, as well as visualizing these data so that you can interpret the results in a very facile manner. So we use both Chem Informatics and Bioinformatics at the center to pull these data together. And as a result of the skills that we've developed over the period that MCCT and CCT have existed, we've been able to build on a very, very solid Chem Informatics foundation. A little bit about chemical substances and how they're represented. So we all know structural identifiers. So you're going to think of things like CAS numbers, names, trivial names, systematic names, UPAC names. People think there's only a UPAC name as a systematic identifier, but there's also, of course, the CAS index name. They can be similar, but you'd be surprised how different they are in some cases. There's all of the trade names for chemicals that are on the market. We have the visual depiction itself. A picture's worth 1,000 words, and you can tell immediately what type of chemical you have when you look at it like this on the left-hand side. We have electronic formats. Some of you will have heard of things like mol files and smile strings as examples. And then you have even the latest one, which has been around almost 2 decades at this point, called the International Chemical Identifier. That's the INCHI, which is shown right here as this particular key right here. So this is the INCHI key. So for this chemical, we have the common name, benzopyrene, we have the systematic name, benzo PQR tetraphene. And these systematic names can be generated algorithmically very, very quickly, fraction of a second. The CAS number is, of course, a lookup. It is registered by Chemical Abstract Services, and there are lots of other common names and trade names. And some of our chemicals have got hundreds and hundreds of identifiers. Some of them actually have hundreds of deleted CAS numbers. They might actually only have one active CAS number, but they can have hundreds of deleted CAS numbers. When you have a chemical structure like this registered into a database, you can use very, very basic informatics to count the carbons, the hydrogens, the oxygens to get the formula right here. The molecular weight can be generated very, very easily because all you're doing simply is doing a summation of the number of times a particular element exists and its average molecular weight. And you can also do monoisotopic mass. These properties here are essential to the work that we do within the center using mass spectrometry to identify new chemicals that we find in the environment, to do targeted measurements, to do non-targeted analysis. There's also measured properties. Measured properties can be measured in the lab in different ways, the different methods. So this is not like calibrating a laser. Log KOW can actually be arranged, depends on who measured it, what the source of the chemical was, the accuracy with which you measure it. But you can get measured properties and put those in a database so that when you search on a chemical, you can pull back these properties: melting point, boiling point, water solubility, bioconcentration factor, and on and on and on. All of value to people who are working in the field of environmental science. But with measured properties, of course, you get to now use those and their relationship to the chemical structure to build models, and you'll hear more about that later. So over here, we have the names and identifiers. We just covered that. We have, this is a mol file right here. This is a representation of the connectivity, the bond order, and if you include the information, you also have the layout. So you can pass a mol file of this nature, and it will give you a nice layout of the chemical so that as you read it into a new application, it will look exactly how you saved it, like this. This is the smiles, and there are many, many different smiles depending on the toolkit that you use. So smiles, as powerful as it is, can be slightly problematic in terms of using it for generic searching across the internet. But then the International Chemical Identifier here is adopted by every online database, really, so that if we're all using this standard, this International Chemical Identifier standard, then linking between these databases can be very, very easy. It has great benefits. So if we now database chemical structures, if we database with them the intrinsic properties, formula, mass, if we add to that database experimental properties, water solubility, log KOW, etc. When you integrate all of that together, then you have the ability from that database and using Chem Informatics tools to start to do things like structure searching, substructure searching, find a particular substructure across many chemicals. You can start to look at similarity between chemical structures, etc., etc. Adding in the other data, that gives you a quick single-click access to lots of data that can be pulled up. If we provide you a way to do that, then you want to be able to download the data. We want to distribute and share our data as widely as possible. So put it into other systems so they can link to us, we can link to them. We're not going it alone. We're actually working in partnership with an entire community of open access science, really. By linking out to other resources, we take advantage of what they're doing by using the same specific standards. It makes things a lot easier. And then as we pull all of this information together, we can focus our efforts to go into specific projects. So specific projects of interest would be the chemicals that have been identified in biosolids, the chemicals that have been identified in wastewater, the chemicals that are identified in hydraulic fracturing, et cetera, et cetera. So the dashboard has been out to address as many of those needs as we possibly can. It's not done, it's not finished, it's never over. As I said, we have done a full rebuild on this. There is a new version that we are expecting to release in November. This version that you have access to today at comptox.epa.gov/dashboard, I will show you a live demo. This version has 883,000 chemicals. The version we're about to roll out is 904,000 chemicals, so grown by over 20,000. And the version that we hope to release in spring of next year already has 1.2 million chemicals. So we never stop growing the chemical collection. By the time this presentation is done by the three of us, be 4 hours in length, the 5 curators will have worked this morning and already added new chemicals. They don't go live immediately, they go live with each release. There are 3 searches accessible from the homepage. I'm going to focus on the chemical search here. Catherine Phillips is going to focus on the product use categories capability. Assay Gene is more on the bioactivity side. We also have this predictions capability right here. Todd's going to go more into the prediction side of things, and you can access both exposure data, chemicals data, prediction data from the batch search right here. So the basic search. This is where you would type in a chemical name of interest. We'll do some of this live, and we are hoping that you will ask questions as we go. If anything doesn't make sense, there's enough latitude in the agenda for us to answer your questions. We'll also go a little deeper at the end of the session with allowing people to ask us questions about specific chemicals. But feel free to play in parallel if you wish. There is a lot to learn. It is recorded, but if you wanted to try a couple of chemicals to come up with questions, please do. Here's an example of typing in benzo-A-pyrene. And this is a type ahead search. So if I typed in bisphenol and I was looking for bisphenol A, it's going to give you a long list of bisphenols until you put space A at the end, at which point it will find bisphenol A. Here, benzopyrene, you can see this string is at the beginning of every one of these names. It is a type ahead search. So it is not finding the string benzopyrene elsewhere in the name. If you wanted to do that, you would want to use the ability to search on the substring. I'll show you that in the next slide. This is a name. You could just as easily type in the CAS number. You could just as easily paste an INCHI key. We'll learn more about the INCHI key as we go, but as I said, it's this international chemical identifier that allows us to link things together. When you see the chemical of interest, you would select it, and it will now dive you deeper into a chemical details page about that chemical. As I said, we have 884,000 chemicals, and I want to clarify that not every single one has a structure. You will see examples of that. Not every single one has a CAS number, but as a result of pulling together 884,000 substances with multiple CAS in some cases, many, many common synonyms, different systematic names, you're going to end up with millions and millions of identifiers. It is not complete. It is impossible to pull the identifiers for every chemical into the system, but we do add them on an ongoing basis. And by the end of this talk, later this afternoon, you will see how you can contribute to doing gap filling. If you see something missing, just like in Wikipedia, if you like, you can help add to that. So this is a type ahead search. I mentioned that you have the ability to do a substring search, and let me show you an example. This is where I want to find every instance of a chemical that contains the term perfluoro. So what I've done is I've checked this little box underneath the search box, typed in perfluoro, and here perfluoro is at the beginning of the name, perfluoro octane sulfonyl fluoride, right at the beginning of the name. But here, of course, it's later in the name. That's why it's a substring search, it's not a type ahead. We have found 2,098 chemicals with the term perfluoro. Does that mean that we only have 2,098 PFAS chemicals? No, it means that's how many names there are with chemicals mapped to them that have the term perfluoro. For the next release, we actually have over 10,000 PFAS chemicals. And then the question is, what do you define as a PFAS? There are many definitions. They continue to change. The OECD has just recently defined their version of what is called a PFAS. So it all depends on definition, but we certainly have more PFAS than 2,000. Not only are we searching for unique structures, but there are ways to go into families of chemicals or categories, if you like. For example, one of the questions at the beginning of creating the dashboard, I went around and talked to people for a number of months to try and see the most basic needs that they would have. And one person said, I would just like to get all the CAS numbers for all of the PCBs in existence. And you would think that would be quite easy. You can certainly get it on a PDF file, but it's not easy to then harvest everything from a PDF file. If you pull out the PCB number and the CAS number, it's not easy then to get the structures because you don't have the structures, you don't have the formulae, and on and on and on. So the reality of it was that became one of the questions that focused us on putting together categories of chemicals and supporting something called enumeration. So this is an example where polychlorinated biphenyls, PCBs, has its own CAS number. That's the entire family. This definition here isn't a simple structure. It's not like drawing benzene or benzopyrene. This is saying that this is a biphenyl. It has multiple substitution points. R1 in any of these positions is chlorine. Of course, it's PCBs, polychlorinated. And then to be a member of the family, you have to have more than one chlorine, and the rest have to be hydrogen. And if you actually sat down and tried to draw that out and try and get all possible variations of that chemical, you will end up with a total of 209 chemicals that match to the set of PCBs. We have ways informatically to do this. So when you represent the chemical in this manner, you can enumerate it to all 209 at the click of a button. You can do the same with polybrominated diphenyl ethers, flame retardants, polybrominated biphenyls, and on and on and on. And it's useful to have this approach for managing surfactants, complex chemicals of that nature. So not just standard structures, but also these Marcuse structures. We also have here a class that is defined. There are many, many chemicals that you would class as polycyclic aromatic hydrocarbons, PAHs. Most of you will have heard of PAHs. But the EPA defines a specific list on the website that says there are 73 in the list of PAHs that we wish to declare. And each of these is mapped directly to this particular class. But there are many millions of PAHs that exist outside this class. I mentioned that once you've done a chemical search, for example, on benzopyrene, you then dive down into the details. And here's where you start to really harvest the data that can be of utility for you in your roles. So there's one thing I need to introduce to you though up front. It's become a very high value for the activity itself. It's become of high value to the community because it is a unique substance identifier. DTX SID right here is the DSS Tox substance identifier. DSS Tox is the underlying chemical registry system and database where we register our chemicals, where we add mappings to CAS numbers, to synonyms, and we map together lots of information such as transformation products, monomer polymer relationships, etc., etc. So DTX, DSS Tox, SID, substance identifier. Each substance has a unique identifier. You will commonly go on Google today and you will find hundreds of thousands of our DTX SIDs proliferating across the world because European Bioinformatics Institute is using them, PubChem uses them, so NIH, FDA use them, et cetera, et cetera. So we're all starting to link based on these substance identifiers. Here's the intrinsic properties I told you about. Here's the structural identifiers, UPAC names, smiles, and key. Linked substances we will touch on in some detail. And then here's the data that you would want to navigate about this chemical. There's also a Wikipedia snippet here. We only have this for about 14,000 chemicals at this point. There's about 2 chemicals a day added to Wikipedia. And I think that having this snippet available, whether you like Wikipedia or not, that's a whole different discussion. Hundreds of millions of people use it every day. And we've worked very hard in the community, not necessarily EPA, but in the community to make Wikipedia chemistry as clean and curated as possible. But to see a little snippet that explains a basic description of a chemical we think of as value. Wikipedia links to this dashboard. The dashboard links back to Wikipedia. Here we are navigating down to the intrinsic properties. When you have a formula like this, the very basic searches, such as find all chemicals that have the same formula as this chemical, is one click. It's very simple. All we're doing is a formula-based search. And click here, find all chemicals, and there you go. Now, for the purposes of analytical chemistry and supporting searches of formulae and mass, which is what our mass spectrometry group does, this type of searching is incredibly enabling for them. And if you look for dashboard papers related to mass spectrometry, you will see that this database has become key to their structure identification elucidation projects. There's a lot more to be said about how we use it for that purpose. There's also that term linked substances, which I showed on the right-hand side below the intrinsic properties. And this is where you want to take advantage of informatics mappings that can be done automatically so that you can find relationships between a single chemical and its many related substances. So, for example, if you have a particular monomer, you might want to find every polymer that monomer is in. These are manual mappings that we have to create. So that's a mapping between a parent and a transformation product, a monomer and a polymer, et cetera, et cetera. But there are some we can do automatically, and this includes things such as mappings between a chemical and its multi-component forms. That could include salt forms, maybe between its isotopically labeled forms that are going to be used inside specific measurements. And how do we identify how these work? How these are done? We do this all with informatics under the hood. You don't have to worry about trying to repeat any of these. It's all built for you. As well as that, we take advantage of the fact that we can do similarity searches, looking at a similarity between a chemical and other related chemicals in the hundreds of thousands that we have. So it's easier to show you what that might look like. Let's take a look here at this central structure. So this is nicotine with no stereochemistry. So we would call this an MS-ready form, mass spec ready, because that's what you would detect by mass spec. You would detect the unique chemical form. You're not going to be stereo specific. You're not going to know whether it found its way into the environment as a salt. You won't know whether it found its way into the environment as part of a multi-component system. So this is what they call an MS-ready form, but it's actually derived from something called Qsr-ready, because for the purposes of modeling, you would also disentangle the salt forms, you would neutralize the chemical, you would remove the isotopic labels, etc. So you would end up with a Qsr-ready form. You'll hear a little bit more about that later from Todd Martin when he talks about modeling. But mapped to this form, so no salt, single component, no stereochemistry, is the L-nicotine, the D-nicotine, the nicotine hydrochloride. This is isotopically labeled. In mass spec, for sure, it will have a different mass, but there's still benefits in mapping to the isotopic forms for the purposes of trying to see what chemicals are in the database of that nature. And then we also have, this is the L-nicotine with a counter ion in a multi-component system. So this all maps automatically. There is a detailed article here about how that come together. When you do that, if you come in on atrazine and you search for related substances, all that linking is done, so you can see multi-component. Atrazine is one component in this. Triazine is one component here. Think of it slightly different way for a moment. If you're looking for a particular chemical of interest, for example, PFOS or PFOA, and you wanted to find every salt form that we have in the database, all you would do is search PFOS, click on linked substances, and it will give you all salt forms that we have registered, as well as chemicals with, for example, waters of hydration, et cetera, et cetera. So all built in one click.
Tony,
Well,
pause for
yes.
just a minute. We have a question. Hi, everybody. This is Molly Jacobs. Just going back for a minute on the DTX SID number, how does that specifically relate to the CAS registration number?
So it's a substance identifier. So one substance will have one substance identifier, DTX SID, but there could be many CAS numbers in the database mapped to one substance. Bisphenol A, for example, has one active CAS number, but I believe has 6 deleted CAS numbers. So it's a one-to-one mapping of substance to DTX SID, but CAS can map many, many times. And we can look at some examples a little later about how things like nonyl phenols can map to many CAS numbers, how that can map to many substances with many CAS numbers. Nonyl phenols in our world is one DTX SID.
Great, thank you. And again, everybody, if you do have questions as the presentations go along, just put them in the chat and we'll be sure to address them.
Yeah, and I'm just putting the URL in here into the chat box in case people want to go along. So one of the other things we have on the details page is details about data quality. We have 5 full-time curators. We have 7 different levels of data from curation. We only have about 20,000 that have been curated to the highest level of level 1. And that's where a human has investigated the chemicals, looking at CAS numbers, CAS number mappings, name mappings, et cetera, et cetera. It does not mean that every single piece of data across the entire page on this chemical has been curated by hand. It's impossible for us to curate every property, every toxicity data point, et cetera. It's just not possible. So this is what it would look like. It's right under here on the record information. And should you ever want to quote some of our data, we recommend that you use this citation. It will tell you the date that was accessed. Underneath the dashboard now, this is not what you can access, but this is how we build up our chemical substance database. This is ChemReg. This is where we build the DSS Tox database. You can see here we've added a chemical. Here's the CAS number. Here's a substance identifier that gets generated at registration. We have some QC notes that can be very, very useful for describing a chemical. This is an indication of how fast things are changing. At one point, this was very representative of where we were in the number of chemicals, but we have already surpassed 1.2 million chemicals. 904,000 is going live in the next release. Just a couple of months ago, we had 910,000 substances. We were still working on curating the 6K. And then CAS made a great gift to the community called Common Chemistry. They donated 500,000 substances to the community, and we have registered 300,000 of those, and we are presently going through the curation around the other 200,000. So we've been able to significantly jump our list. How have we done that with CAS? CAS made a decision to release chemicals of interest to the community from specific regulatory lists. So things like TSCA, as an example, they released the entire set out to the community with structures, and that's been very beneficial for us to grow our data set. But you can see that our highest level, which is now approaching about 20,000, it's very, very slow how we can manage to eke out these highest level of curations. It takes a lot of time for us to get to the highest data quality. If you want to know the history of the entire database, this was started by Anne Richard at the EPA almost 2 decades ago. It took a number of years to get to 5,000 chemicals. Then one of our colleagues, Chris Grolke, joined. He was an informatician. He grew it to a few 100,000 by harvesting public data and putting in place some good data checking. Sadly, Chris is no longer with the agency. He's moved on to other things. But this is the real history of what underlies the dashboard. I commented that you can contribute to the information. So for example, if you're searching for a chemical name, a synonym, and you cannot find it mapped to a certain CAS number, you have the ability to click on submit comment here and give us the particular input. You would enter your email address, prove you're not the terminator, and hit submit. And that piece of information will come to us. We will respond to you with our feedback on your comment. And all of the comments ultimately go public, but without your name, so people don't know that you're the one that reported it. But we do like to make the comments public. I will point out here that for xylenes here, this is another form of ambiguous structure representation where this annotation says the methyl could be ortho, meta, or para. So diving down now, once you get to a chemical substance, you start to dive into the data. So this is the executive summary page where you can dive in and find whether or not there's cancer information available, whether there's iris values, whether there's reference doses available. And we're going to do this through a live demo. So this is executive summary. This is going to allow you to dive into the physicochemical properties. And we use different ways to predict these properties. We have both commercial tools from ACD Labs. We have EpiSuite, estimation program interface, which has been around for over 2 decades, funded by EPA. We have Todd's tool, toxicity estimation software tool, test, and we have Opera that came from one of the. All of these get predicted. When we have models available for the endpoint, we put the experimental data up as well as the predicted data. And there are many different types of predictions available. You have the Qscr, which is the activity relationship. You have property relationships, QSPR, and you have Qscr, which is what Catherine Phillips will be talking about later. She built the Fuse models. Todd Martin will cover this in more detail later. We also take advantage of the fact that we can map between chemicals. So as I said, we share data. And in this case, what we've done is registered our data directly into PubChem. And when we do that, we get a PubChem chemical identifier back. And when we have a mapping between both sites, we can pull their data in real time. So this is pulling their GHS data. There are 6 different countries and databases that have contributed GHS data for benzopyrene. This loads in real time. We pull it from PubChem. So if PubChem goes down, it won't show. So that's a hyper dependency, but it's so beneficial that they've done that contribution to the world and we get to take advantage of it. There's the Toxicity Database. This is built by Richard Judson and contractors that he's worked with and postdocs. This gives you access to both human and ecological toxicity data. This is what's presently available in the existing version. So there's 50,000 chemicals, 770,000 toxicity values. Out of the 884,000 chemical substances we have, not every single one has toxicity data. The 884,000 substances we have, not everyone has Qscr data because there's no structures, so we can't predict them. If you look at the TOSCA inventory of active non-confidential data, there are 34,000 substances in the active non-confidential set. 16,000 of them have no structure, so we cannot predict properties. They're UVCB chemicals. But the 70,000 citations, 5,000 journals, we will take a look at this. Anyway, you see a table such as this, you can always download it. So your download button allows you to download an Excel file or a comma separated or tab separated file. We also provide access to something called SDF files. I showed you at the beginning that thing called mol file, which is atom-atom connections, bond order, stereochemistry, and layout. The SD files are a way to download 1,000 chemicals in that format so that if you have Chem Informatics tools, you can view them at the desktop. Catherine Phillips will cover the exposure data in more detail later. A little bit about the bioactivity data. This is going to be rather fast. I'm not sure how much interest this particular group will have in having the bioactivity data, but we can dive into it a little later in detail if we need to. There is an article on the ToxCast work. This was written by Anne Richard and so many of the centers who contributed to this. This is almost 2 decades again of work that has gone on. I think it's approaching 15, 16 years at this point since this started. It's a brilliant paper outlining how the ToxCast project has been led. and how much data has been generated on thousands of chemicals. Now we have 884,000 substances in the dashboard. 8,000 plus of them have been through the TOX21 bioactivity measures, and this is a limited number of assay endpoints for a large number of chemicals. So that's TOX21. We are a part of that, working with the FDA and NIH. But then we have the other project, which is EPA-led, which is ToxCast. And ToxCast is over 4,000 chemicals, but a much broader distribution of assays, probing an awful lot more biological endpoints. If you want to see the types of lists that we have available for these 884,000 chemicals, you can come into the chemical lists functionality and take a look at what's available. So in this case, I've come in at the list interface and I've typed in ToxCast, and it gives you the historical breakdown of how these chemicals were run through the ToxCast and TOX21 assays over the years, how they were selected. That paper tells you all the details, but we have segregated the chemical collections here for you to browse through. I think more of the interest for you will be on things like the lists that has flame retardants in it, a project that Catherine Phillips and I have been involved with of late, and things like hydraulic fracturing, pesticides, etc. The bioactivity data never stops being generated, so we're always adding new chemicals. There'll be new bioassays that are measured to probe different endpoints. And the last version that we have public in this version of the dashboard, it was released in August 2020. There are a total of 17 different assay sources that includes commercial assays that we fund in order to get these measurements made, as well as our own laboratories inside the agency, where our own laboratories are measuring these thousands of chemicals against different assays. And for TOX21, as I mentioned, we have over 8,000 chemicals that have been through the TOX21. You can see that particular list here. Looking at the data for a particular chemical that's been studied, 884,000 substances, but only 8,000 through TOX21, 4,000 through ToxCast. You will find this bioactivity data will be active here. When there's nothing available, it will simply be grayed out. And here you're seeing the data that's been measured on bisphenol A. This is just a visualization of the data that's available. The fact that some of these points are highlighted in the interface, they actually flash. And it's because I'm hovering over these visualization elements right here, and it is showing that there's a lot of response for nuclear receptor assays. Not unsurprising, it's bisphenol A, so think about endocrine disruption for bisphenol A. The data are much more detailed than that. The bisphenol A was studied in 1,152 assays, was deemed to be active in 217 of those assays. And this table structure here, with one click, you can download all of the data directly into an Excel spreadsheet, but you can see the types of target families that the ToxCast and TOX21 assays are probing. You can also see association with specific gene symbols. These are manual mappings that have been made between those people who understand why a specific assay was chosen, what was the target that was being investigated. There could be a series of targets, of course, was being investigated with a particular assay. The details of how the assay was measured is right here on this model. This will literally tell you how it was measured, what the reagents were, the time scale of the assay. So much detail sitting one click away to give you full transparency to what was measured, to the point where as you scroll down into the activity data, you actually see every single dose response curve and every experimental data point that was measured for a particular assay endpoint. Lots of detail here. This would be a big dive into this. And this is, as I've just mentioned, 217 active responses for 1,152 assays. And if you want to see all of the data, you can show all of the inactive data too. What you would make from these data as you dive down into it. By the way, this work is being conducted by a number of our scientists over the years. So Keith Haug, who's no longer with us, sadly, he retired. Katie Paul Friedman is presently responsible for overseeing the in vitro DB database. Richard Judson has been involved with modeling the data for a number of years. And when you look at the data for a particular chemical, you start to see responses against specific target families. And then you can start to see that there are specific endocrine responses, as an example, against the estrogen receptor or against the androgen receptor. But people like Todd can model these types of data. Richard Judson has written models. Todd has gathered model data from the literature and built his own models. Collaborative teams across the world have used the ToxCast and Tox21 data to build models, which will actually show up. I think I have a slide on that shortly. And if you want to probe down into a single individual assay, you can look at the set of chemicals associated with a particular assay.
Tony, there's one question about how do we get data of the assays which are actually not in the dashboard after the recent update?
How can we get the data of assays which are not there in the dashboard after the recent update? I'm not sure I understand the question. We release the in vitro DB data on a schedule. So 3.4 is about to be released in the next version of the dashboard. The entire SQL database dump will be available from an EPA website, so you can download it. But there is certainly a time scale at which we release the data when we've processed it, reviewed it, validated it, and ready to release it. I'm not sure if that answers the question.
Sudha, if that didn't answer your question, if you want to just unmute your line and ask it a different way.
We can also come back to it in detail later, because at the end, I give you a review of where to obtain our data for download, et cetera, et cetera.
Great. So why don't we pause on that then, Sudha?
Browsing through the data, we have lots of visualizations and ways to review the data that's available for you to download. I will talk about this in more detail at the end. And as I said, we have pulled together so much data over the years, and there are various models built around this. Two of the most well-known are the SERP and that are available, published on a number of times. And these data, we then use these models to predict for other chemicals in the dashboard, when we believe these chemicals would be active against the estrogen receptor and androgen receptor, and they are reported in this ToxCast models subtab right here. Anywhere you see an informational icon on the dashboard right here, you can hover over it and it will take you to the peer-reviewed publication. It will tell you a lot more about how the models were developed. We can't give you all details in the interface here, but we always lead you to the details. And I believe Catherine will show you how that is true for the exposure. So you will see these informational icons scattered across the application, and they're there to help you understand how we do things. And I mentioned, Catherine will go through product use categories, and the bioactivity data you can probe and search based on a particular assay or gene. If you're looking for a specific assay vendor, you can search it right here. If you're looking for a specific target, you can search it through the assay gene search right here. Generalized read across, we will likely come back to in more detail a little later in some of the future work section. But I want to show you that this is the generalized read across module that was developed by our colleagues, Grace Patlowitz and Imran Shah. And this allows you to take advantage of the toxicity data that's been assembled. The fact that we're using informatics approaches, using things like similarity searches to find chemicals that are similar to your chemical of interest. And then it pulls together the bioactivity data, the toxicity data, and tries to predict toxicity for those chemicals against specific endpoints. So in this case, you're looking at chronic toxicity, abdominal. What it's done here, this is my chemical of interest. It pulls back chemicals that are similar to it based on chemical structure. You can also do this in tandem with bioactivity for those chemicals. This is pulling back a matrix of data. that are associated with these chemicals that are similar. And then this is showing you that black means active. This is 0-1 binary display of the data. So where there's activity against chronic abdominal toxicity, adrenal gland, et cetera, et cetera. Actually, this is just showing the availability of data. The next phase will actually generate the data matrix and tell you about active or inactive. Genera itself would be probably an hour-long presentation, but you can come to this particular application and anywhere you see these informational icons again, you can actually play a video that will teach you how to use Genera. There's a lot of publications on this. It continues to expand in capability, and they've been working hard on adding in of late physical property influence on read across, as well as trying to incorporate transcriptomics data that we've been measuring inside the center. So I showed you single chemicals, and we do have a certain amount of data available in the dashboard, but I've said what we want to do is help you find other data. So the internet is a big space. There's a lot of databases out there. So because we've harvested all of these synonyms, CAS numbers, names, etc., into a synonyms table for a chemical, you can see that there may be a lot of chemical names, literally hundreds. So what we try to do is use these synonyms to support other searches. So for example, we link up to Google Scholar, we link up to PubMed, we link directly to IRIS using CAS numbers and names. We can push these out to do other searches. So for example, land on a chemical, click Google Scholar, it will use the CAS number and the name, and you can select a particular type of query you want to do, and it will pull these data directly. Of course, you could do this yourself in Google Scholar. By making use of our chemical curation, you're using our CAS numbers and names to push it over. This is an IRIS linkage. So when we have integrated risk information system reports on chemicals, one click, and we load the IRIS report into the interface. In PubMed Abstract Sifter, what you can do here is take advantage of the fact that we have CAS numbers, names. We push these out to hit a web service running on PubMed. A web service is a programmatically accessible interface where we can send a query directly against that. So what we've done here is we're saying for benzopyrene with this CAS number, push the CAS name and run me a query based on hazard data. So it appends this particular query that comes from a database. It will hit PubMed in real time, hits 30 million abstracts, and pulls back the data for us to review. This filtered and reviewed, we'll show some of this later on. And then external links, we're now taking advantage of the fact we have CAS numbers, names, INCHI strings, smiles to link up to over 70 public resources, single button click. In this example, we can go to the EPA website with one click. We can go to Chemble. For the same chemical, we're just doing these queries. We're going out to these sites. Similarity searching is going to come up a little more later in terms of how we represent chemicals for things like the hazard comparison dashboard. We have got aspects of structure search, similarity search, but this happens automatically in the background. You come in at a chemical level, it will do a similarity search for you and display chemicals that are similar in chemical structure. I mentioned mappings between polymers and monomers, between substances and their transformation products. These are mappings that are made by our curators so that you can find these chemicals, these related substances with one click. And then chemical lists and categories. At the top of the page, you have lists of chemicals, and here's an example of extractables, and leachables. So when we work with different groups, they will provide us lists such as pesticides, extractables and leachables, the ToxCast inventory, etc. And we build these as subsets of data. And I'm going to move into the batch search shortly and then show you that live. If you're interested in PFAS, we have the largest single structured set of PFAS that we're aware of online today, and they are segregated into lists. So if you're working on specific methods, you can find our methods lists here. You can see what we've purchased and what will be screened through our bioactivity measurements. So find any list of interest, for example, pesticides here. I will choose my pesticides list of 4,000 chemicals. It will describe where that list came from. It will give you the link to the data site if it's available. And then what I'm going to do here is take this list of pesticides and send it over to batch search. So single chemical searches are great, but most of you are working with lists of chemicals, lists of CAS numbers, lists of names, et cetera, et cetera. So how would you get all of the data that you'd be interested in from our website? If you wanted the test predictions that Todd will be talking about, if you want to know if there's exposure data that Catherine will be talking about, if you want to know if things have been measured in ToxCast, how would you do that for 1,000 chemicals? So that's why we introduced the batch search. And in this case, I'm showing you an example of the batch interface right here, batch search. I've pasted in a list of chemical names. It's also got CAS numbers, so I'm feeding in both. And then all I'm going to do is choose what I want to download. Maybe I want formula, mass, whether there's toxicity data, whether or not there's an iris report. I can select in this interface whatever I want to download. I can do the same just for a list of CAS numbers, which most of you will be working with. Select the data of interest, and then it can, with one click, and depending on whether it's 1,000 chemicals or 5,000, it can take a few seconds. It can take a couple of minutes. We can download this entire spreadsheet. So it's literally going to be a few seconds to a couple of minutes to assemble everything of our database into a format that you can interrogate and store locally. The DTX SID, that substance identifier, is stored and hyperlinked in the spreadsheet. So in the few minutes I have left, I'm going to quickly switch over to the public dashboard, and I'm going to start with a list. So when I go to lists of chemicals, I'm going to choose something now that would be of interest to maybe to many of you. So let me go to LC, extractables and leachables. So here's a set of chemicals. So I saw that there was somebody who was attending, had some details in the spreadsheet, what their interests were. So each of these chemicals here is part of the LC list. The LC list came from the Extractables and Leachables Safety Information Exchange. We manually curated the data to make sure that the CAS numbers, the names, the structures all matched together. Every one of these is hyperlinked. So if I want to see the data for a particular chemical, I can click on it and see that chemical. So this is now going to pass this DTX SID over and load the information. And as I mentioned, we have the executive summary. So benzoic acid, they will now try and pull the data from multiple databases. There is an iris value available. Click here. There's my iris report, and that's what that's done is navigated down the tabs. We have minimum RFD values. That's going to come from the hazard tab right here. So these are the data that are available. We've got 71 records from different sources here. This is from Euclid. This is from EFSA, Cosmos, ToxRefDB. So all the sources that we have. These are point of departure data, tox data, screening level data, and we have both human and eco data. So Department of the Environment, eco risk. So you can harvest these data easily with an Excel download. Every time you see a table, you can download the data. So you can see how easy you can pull it off the application. Back to the executive summary. We have regional screening level data shown here. We have these flags are telling us we have reproductive tox, chronic tox, subchronic, dev tox, et cetera, all sitting in the hazard tab. So this is where you would find your toxicity data that you can scroll through. And of course, if you're a little puzzled as to what a particular type of data is, you can hover over it. That's the executive summary. We also show you on this one page as much as we can about the chemical in terms of phys chem parameters, point of departure plots for both oral and inhalation data. And if we have bioactivity data, it is shown in this plot right here. But this is just the summary. The property data that I showed comes from this property tab. Todd will cover this in more detail. We also have fate and transport data. The safety data that I mentioned that we pulled from PubChem is right here, pulled in real time. Exposure data. This is what Catherine will be going through in some more detail. Just pulling product use category data, chemical weight fraction data from particular products. The bioactivity data that I mentioned. Here's all of the plot in terms of the toxicity, in terms of the bioactivity data that's been measured, as well as, so benzoic acid was studied in 857 assays with 13 active. These are similar compounds, so it's doing a similarity search across the database to find similar compounds, and we can filter out things like isotopes, etc. Synonyms for benzoic acid, there are many. 51 records. There are 2 deleted Cas numbers, maybe more. No, 2 deleted Cas numbers for that. Here are the links that I showed you, where I can link out to many different sites. So if I want to see the substance registry service from EPA, we link out to that page. Sorry. So back to the overall data set now. So all of the things that I was just showing you, toxicity data, bioactivity data, property data, consumer products data, that's what you would want to feed into the batch search here. And I can do it one at a time. T, atrazine, etc., toluene. So you can do this and try and find the data. But if you're working on a particular list, and I imagine that some of you will have interest in extractables and leachables, you would send that to the batch search. And now all we're going to do is choose what data we would like to download. I would like to grab the Cas numbers for every chemical. I would like to download the UPAC names, the SMILES, and whether or not there is toxicity data available, whether or not there are, how many PubMed articles, this is a snapshot in time, and whether there are IRIS reports. And I could expand here what I would like to download, but I'm going to just click download and stop there and wait to for a couple of questions while this is downloading. I will answer the question that just showed up from Topher. The media question, do you employ any tricks to prevent Excel from interpreting Cas RNs as dates? Yes, so we force out the Cas numbers in a text format so that you can, so that they do not get corrupted. But Topher, we also have ways of checking on Cas numbers. So let me show you a couple of the things that we have to do to ensure that we get correct. I'm going to go back over here to batch search again. This is a Cas number for bisphenol A, but if I happen to type that incorrectly, all I've done is transpose 0 and 5. I will get that Cas number. It still looks correct, and maybe a 9 instead of a 7. So here we know what Cas numbers should look like. We know that they should pass a checksum. Maybe people on this call don't realize that a Cas number has a particular checksum. This checksum is based on calculations done between the first 2 blocks. So we check Cas numbers. We know whether they are correct or incorrect. And of course, we are making sure that these do not turn into dates, which is a very, very common problem for when we're dealing with these. When we get Cas numbers from people for lists to register, we have to be careful with making sure that we import these correctly. Chumbo Zhang is acting. What does active mean for the assays in the search? So there is a threshold of activity that is set depending on what the actual specific assay is. That threshold is set based on the specific assay. We do multiple curve fittings. In the previous release, we did 3 different types of curve fitting. I think now we're doing up to 5 in the latest release. And if that particular threshold is passed for the dose response curve, then we will flag that as active. But you have the ability to dive deeper into the dose response curve data to see whether or not it passes the threshold for you. But activity means it has a response for that particular bioactivity measurement for that particular assay. And every single one of those is detailed in the modal that I pointed out. Thank you, Meg, for pointing that out, where the checksum is. And here is the Excel spreadsheet for all of the chemicals, the 457 chemicals that were downloaded for the LC list. Here's the hyperlinked DTX SID. Here's the names. Here's the CAS numbers. Here's the UPAC names, smiles, et cetera, et cetera. So that is 457 chemicals that came to the batch search and pulled that information down. We'll do some more of this demoing if we have time at the end. But are there any other questions before we take a short break? The short break is introduced as a bio break for people. I can certainly keep showing things for the next 5 minutes if people want to take a break. So it's up to you.
And also, do know that we are recording this. So if you want to go back and review this at your leisure, you'll be able to do so next week.
Sounds great. So why don't, for those of you who need to take a bio break, it's 12:12. Why don't we take a 5-minute break? Anthony, if you'd like to keep speaking, and this is great. So many resources, and it's quite amazing while people are on a break. But we'll, after you go through a few more minutes of showing off stuff, we'll move into Qscr modeling approaches with Todd Martin. So why don't we'll reconvene at 12:20. You'll just get an extra 2 minutes so we can round it up. This seems kind of odd to start at 12:18. So we're going to restart again at 12:20. If you'd like to keep showing off the stuff, Anthony, I know so much work went into it. Those of us who are still here will be happy to watch it. And as Molly mentioned, we will be posting this on the A4 website within 2 weeks. So because so much information was presented, it's great.
Okay. All right. Well, I will keep going then. So let me share my screen again. All righty. So would anybody care to put a chemical name in the chat box, something that you're interested in? If not, I'm just gonna go. So let me show you a little bit about the substring searches, because I think UVCB substance, silicon or silicone. Let's do a substring search on silicon. Oh, fipronil. All right, so let's go fipronil. All right, so I'm going for single chemical fipronil. And Cooper Doherty is almost certainly interested in things like ADVAC, I would imagine. So fipronil, and we will do a UVCB substance for sure. So we've searched here on fipronil. Here's the Wikipedia snippet. Here are the intrinsic properties. If somebody was trying to detect fipronil, what forms do we have? It's a very unique formula. So we found fipronil itself, and we've found the R and S forms of that particular chemical. So the stereo forms are right there. Linked substances. So there are 17 records that are similar in nature, similar structures. What I just did there was I came from the details page, I came to linked substances, but by selecting this similar compounds, it links directly over here. Here you can see fipronil similarity compounds, and what I'm going to do is switch off the isotopes. This is deuterium labeled. This is C13 nitrogen 15 labeled. This is the sulfone So I'm going to hide the isotopically labeled that reduces it by 5. And now you see a set of chemicals that may be similar in nature to what you want. I'm going to switch off multi-components. That's going to remove the salts. And now what we have are a set of chemicals that are similar in structure to fipronil. Now, what would be ideal here, and I think we have this in our latest version, is fipronil has related chemicals based on degradation, transformation, etc. So we would have those mapped up over here in the related substances tab. I'd actually like to show you an example of that. So if I go to chlorothalonil right here, chlorothalonil has been measured, its breakdown products in the environment. And when we read through publications, we try to find transformation products. And these are mapped to the DOI for the article. That's not publicly available yet, but we have it in the database. And in a future update, we intend to give you the direct DOI to the article. But this is chlorothalonil itself. These are all transformation products detected by mass spectrometry. And you will find things like this in related substances. I'm going to go for a moment to, let's see, add back. So that was a question about the quaternary ammonium compound. So here's an example for benzalkonium chloride. So this is a UVCB. Notice no structure. And remember I said no structure means no Qscr, no QSPR. We can't do structure-based predictions, but in this case, we have related substances. So here is an example component, one of the components of that chemical. And that, of course, will have, because it's structure-based, it will have predictions. So you will find there your properties, your predicted properties, fate and transport, predictions, etc., etc. Somebody has typed in a particular CAS number, 55406-53-6. So carbonate preservative that extracts a lot. So iodopropenyl butyl carbamate, water-soluble preservative used globally. So that's why I would not know anything about that chemical. I think a Wikipedia snippet becomes very useful for that. I don't know what exposure data might exist for that particular chemical. So we'll drop down here. So it's telling you it's used in hand and body lotion, shaving cream. It is associated with Weather Shield exterior, skin. Yep, so there's the Gillette series, shaving foam, etc., etc. And it appears, okay, so not on TRI. I think they've changed their link right there. You pick up REDS, registration eligibility decision. I've never heard of REDS, but what we could do here, let me show you how we take advantage of external links. So I think I copied the page that you provided, but it's not taking me to that. Find me a new page that would give me that we can see.
I'm looking. Yeah, that would be great. So for many of us that are searching and characterizing alternatives or looking for, this one's a water soluble fungicide that it's a sensitizer and it's not good, it's water soluble in certain products. We often will data mine old registration eligibility decisions. So it'd be nice to kind of be able to pull those in so we don't miss it, because they're sometimes for some reason hard to find. And then the web pages keep changing. So whenever I assess this, created a TI, or my coworkers did, it's now been changed. Yeah, like this one. But that would be great if it could, those get swept into your database too, because there's so many of them and they're a wonderful source of tox data.
So the way that we do this stuff is we do it through these external links, as I mentioned. And what we're doing is we are linking SMILES in certain cases. So if we want to do a prediction, we pass the SMILES and it does a prediction. We use INCHI keys in some cases, CAS numbers in others, etc., etc. So what we would do is we'd form a link here to the relevant EPA website. So for example, ChemView should work. What we do is we pass the relevant identifier over. So I've never heard of REDS, maybe Todd and Catherine have. We have so many websites at EPA that are, even 6 years here, I'm still learning them, honestly. So, but let me see here. I will show you the benefits of an INSHI key, and then we should go back to the agenda. For this chemical, this INSHI key here, which is generated for every chemical that we register, becomes becomes a way to search the entire web. So right there, what I've done now is I've searched the entire web. I've structure searched the web for that chemical. And if I take that, I wonder whether or not it's got it on PubChem though. It's got, oh, pesticide registration status. What we would need to do is download these chemical names and the links to this page. So that's a manual task that we'll do. I'll look at that and get back with you on that. All right, I'm going to hand over now to Todd's up next. So I'm going to stop sharing and go on mute and let.
We can see you just fine, Todd.
Okay. All right. All right. Is it showing my main slide?
Not yet.
Nothing yet. No, nothing yet.
Oh, I didn't hit share. Hold on a second.
Yep. And if you just put it in presentation mode, yep, perfect.
Okay. All right, we're good. Okay. Today I'd like to talk to you about US EPA Qscr prediction and hazard comparison tools. Give a brief outline of my talk. I'll go over the basics of Qscr modeling. Then I'll discuss some tools to estimate toxicity or physical properties. The main one I'll focus on is TEST, which is the toxicity estimation software tool. And I'll briefly discuss Opera, which is the open structure activity relationship app. We also have access to EPA's EPI suite, which is kind of a legacy tool for predicting toxicity and physical chemical properties. And then finally, I'll talk about the tool that one of the tools I've developed to compare chemical alternatives, which is the HCD, which is the hazard comparison dashboard. Just to give some basics of Qscr modeling, Qscr's quantitative structure activity relationship. Essentially, you take a molecule, you convert it into a numerical representation known as a molecular descriptor. And once you have molecular descriptor values, these are like independent variables which you can use to correlate a toxicity endpoint or a physical property. So you can visualize it as a simple multilinear regression equation where this is the toxicity is the property you're trying to predict. A0 through AN would be fitted adjustable parameters like regression constants, and X1 to XN would be your descriptor values. So it's just, you can, and it's in the simplest case, it's a single equation to predict the toxicity. What you do is you build a overall data set for modeling, and you randomly split it into a training set and a prediction set. You fit your model to the training set, then you generate results for the prediction set, then you calculate statistics for the prediction set so you can see how well your model did. And typically people come up with different domains of applicability to decide whether or not to trust a prediction for a given compound. So they call that domain of applicability. So I'll just cover that briefly because I don't want to get too down into the weeds in the science of this, but mostly I just want to show you the tools that we have available. Just to give you a flavor of what's in the test software for predicting toxicity and physical properties, we have several different Qscr methodologies that are built into it, and then it's fully automated so you can run them all at the same time. There's what I call a hierarchical clustering method, a single model method, a group contribution, nearest neighbor, and consensus. And I'll go through each of these in turn, but I just want to show you that there's a bunch of different methods that are available in this tool. And there's a user's guide in a PDF form when you download the downloadable test application, which will go into detail on all these different methods that you have access to. Just to show you, conceptually what it's doing in the hierarchical clustering method is if you have a data set with a bunch of different chemicals, you can use the different descriptor values to cluster different chemicals together, like different similar chemicals get clustered together. So then you get a series of clusters from your data set. Then you can build models from different clusters that you've constructed. Of course, you wouldn't build a model unless there's at least 5 chemicals in a cluster. And then when you want to make your final prediction, you take the average of multiple predictions from different cluster models. And each cluster model is a multilinear regression model. So what this is doing is basically you're trying to develop a series of models to predict a chemical rather than just using a single equation. And the advantage of this is that you're not relying on any single model to make your prediction. Like a lot of people use like class-based models where like if you wanted to make a prediction for an alcohol, you'd use a model that's fit to just alcohols. Whereas this approach, it allows you to use all the different data in the data set so that you'd be able to make a prediction for a chemical that say had an alcohol and an amine in the same molecule. But if you're only using a class-based approach, you wouldn't be able to really decide which model to use. You'd probably have to make a prediction from an alcohol model, an amine model, and take the more toxic value. And that's the approach that EPA's EPI suite uses, is that it just basically takes the most toxic prediction out of the appropriate class models. So anyway, this is a more sophisticated approach to try to utilize all the information in the data set. So moving on, a single model in the test software is basically like one of the models that's in the hierarchical clustering. So basically you just fit a multilinear regression model to the entire data set, and you got a single multilinear regression equation. And like, for example, this would be the equation to predict 48-hour Daphnia magnet LC50. So it has, your fitted coefficients and then your molecular descriptors. And it's pretty easy to visualize. And that's why I kind of kept it in the test software, because you can see it in a single equation and it's just kind of useful. Moving on, group contribution is the same basic concept as the single model, except that you're using molecular fragment counts as your molecular descriptors. So for example, if you had ethanol, you could break ethanol down into a CH3 group, which CH3 group is here, a CH2 group here, and an OH group here. Then if you add up the contributions from each of these fragments, you can use your multilinear regression equation, and then you could calculate your toxicity value. So it's a very simple approach, and it's kind of easy to visualize, and you could do it in a spreadsheet if you wanted to. And so this one, it's just kind of cool because you can do it pretty easily, and you could do it on, if you can do it in a spreadsheet, that's pretty cool. So anyway, I don't think it has as good of an accuracy as some of the other methods, but conceptually it's kind of cool to show people. Nearest neighbor method is basically an analog read across approach. So what you do is if you want to make a prediction for a chemical, you just find the 3 most similar chemicals in the training set, take an average, and that's your prediction. So if you want to make a prediction for benzene, these 3 chemicals would be the most similar. Then you just take the average of the toxicity of those, and then boom, there you go. There's your predicted LC50. And the nearest neighbor approach it's kind of like the lowest accuracy, but it's really quick and dirty. And you can also see immediately what chemicals were used to make that average and make the prediction. So again, it's just conceptually kind of cool to be able to show people, okay, well, here's the analogs we used, and here's the value. So, and then finally, the consensus model basically takes all the models in the previous slides that I showed you and just takes a straight up average. And what that ends up doing is it ends up dampening out any really bad predictions. And it only makes a prediction if at least 2 of the models have a valid prediction. Because in some cases you could have a chemical with a really exotic structure, and only one of the models makes a prediction because it's inside the applicability domain. So this second bullet point here kind of makes sure that we don't have a really exotic chemical. So we only want to make a prediction if at least 2 of them made a prediction. So the goal of this is basically to be able to get the best accuracy and get the most prediction coverage. When I say prediction coverage, that's like the fraction of chemicals that can be predicted. So that's like the default, the default prediction that we show people in our tools is the consensus model of multiple models. In the future, we're working on moving on to different QSCR methodologies. There's a lot of things available out there in the literature and software packages, and like in Python, like scikit-learn is a big Python machine learning language. Library. And so there's different machine learning packages out there. So we want to add things like random forest, support vector machines, deep neural networks, XGBoost, and so these approaches are really fast to learn, and they get really good accuracy. They're a little more black box in that you can't quite see the equations like you would in the methods I showed you earlier that are in the current version of the test tool. But these have the potential to get much better accuracy, and we treat this as like our next generation of all of our tools is to use these kind of models. And the cool thing about a lot of these is you can deploy them as web services, so people can just go in their web browser, put in a smile string, and then get the predicted value from some of these. So our current tools have web services too, but these lend itself to make the coding for these is a lot simpler. Okay, where can you get these different tools? Initially, I developed the test software, which is a downloadable Java application. If you go on the internet and you search for EPA test Qscr or whatever, and you should get this link to download the Java application. We have a web version on the dashboard. So if you go to the main dashboard page like Tony showed you and click on the predictions tab, that'll take you to there, and I'll show you that in a minute. And we also have stored predictions on the dashboard. So if you search for a specific chemical, you can dig down and you can get to the predicted value. And these are like the cached predictions for all the chemicals that are in the dashboard. So it's not, the third one is not doing real-time predictions. It's just a stored value in the database. But I'll show you each of these in turn. This is what the downloadable test Java application looks like. And then here's the link to that, like I showed in the previous slide. You can search for, it has a built-in database that you can search, and it's like an offline database. You don't need the internet. So you can search by name, cast, smiles, SID, name, and it'll generate a structure here. You can pick which toxicity endpoint you want to predict, which Qscr method you want to predict. Again, the consensus is the default. It has some extra options, but I don't want to get too down into the weeds. You can pick where you want it to output, you click calculate, and then you'll get your prediction. And it also has a batch mode. So I'll show you that later. But so it's very simple. You search for your chemical, you pick which thing you want to predict, click calculate, and you get your results. This is what it looks like if you go to the dashboard and you click on the predictions tab. It gives you the web test, which is basically it's the same basic thing. It's just done in a web browser. So you can search just like you did in the other one, get the structure displayed, click calculate, and you get a table of predictions for all these different toxicity values and physical properties. All right. If you go to the dashboard and you want to pull up the pre-compiled predictions, you can go to the main dashboard page, which is here. You can search for chemicals. I've searched for this chemical. And this is the main page you get. And if you click on the properties tab in the top left, you get these experimental and predicted values. If you click the little drop-down box and switch it to water solubility, then you can finally start to see the predicted values. So in this little table at the bottom, there's the test prediction, the prediction from ACD Labs, there's OPERA. For this particular chemical, there wasn't, for whatever reason, there isn't an EpiSuite prediction, but normally there would be an EpiSuite prediction here too. You can access the test prediction report. You can click on an OPERA report, which basically details on the prediction. And for OPERA, we also have a QMRF document, which basically it's a long PDF that describes all the different details about the model and how it was built. In the future, we'd like to have a QMRF for the test as well, but that'll be future work. So this is kind of what the test prediction report gives you. Just ignore that little A symbol. I don't know why that's there, but it gives you the main predicted value. So like the experimental value is 1,400 milligrams per liter, and the predicted value is 5,300 milligrams per liter. And then it gives you a summary of the different predictions from the individual methods that were used to define the consensus value. Because this value, this row right here is this is the consensus values right here, and these are the experimental values. And then these three are averaged together to give you the consensus. So if you take an average of 1.36, 1.92, and 1.31, you should get 1.53. So that's the consensus value in the units of negative log base 10 mole per liter. Most people like to look at it in terms of milligram per liter, so that's this row. If you scroll down in the prediction report that you get on the dashboard, it'll also show you results for similar chemicals in the training set, because sometimes people like to say, well, was this chemical that we're trying to predict, is there similar chemicals in the training set? So we can get a little more confidence in the predicted value. So if you look for the chemical being predicted, there are fairly similar chemicals in the training set, and they were predicted well. And if you plot the experimental versus predicted for the similar chemicals in the training set, they're pretty much fall on the y equals x line. And the mean absolute error is 0.27 log units. And then the mean absolute error for the entire training set was 0.5 log units. So similar chemicals were predicted well compared to the overall data set. You can also look at similar chemicals that are in the external test set, because sometimes people trust that more than the similar chemicals in the training set because it's an external prediction, whereas chemicals in the training set should normally be predicted well because they were used to fit the model. So for this particular chemical, there's two chemicals in the external set that are similar enough to display here. Like they need to have a similarity coefficient greater than 0.5. So these two chemicals were, I mean, it looks a little off just because you're zoomed in, like you're only between 2.5 and 3.4, but the mean absolute error is only 0.26 log units, so it's not terrible. So that's the results for the external test set similar chemicals. In that previous slide, I showed you can access the opera prediction report for this chemical on the dashboard. So it shows you the details on the model for a water solubility, and it shows you the nearest neighbors from the training set. So that's kind of similar to what I showed you before from the test report, where this is showing you the nearest neighbors from the training set for the opera prediction model for water solubility. So we're trying to predict this chemical, and these are the similar chemicals in the training set. So it's a similar kind of deal. And this shows you what the opera QMRF looks like for boiling point in this case. But it has, if you scroll through the PDF, it has all the details that you'd want to know about the opera model for boiling point. So, but that's on the dashboard for that chemical when you dig down into the predictions page. Now I'd like to switch gears and talk about alternatives assessment. Alternative assessment, the goal is basically to identify safer alternatives for chemicals of concern. So if you have a chemical for a certain purpose, you'd like to know, okay, well, what else can we use for this application that have less hazard? When people do alternative assessment, there's usually two different ways they're doing it. The first way is comparative chemical hazard assessment, which basically just looks at the different toxicity values for the chemical of interest. And then other people look at, in more detail, they look at exposure assessment, like how are people being exposed to the chemical. So, you know, if something is toxic, but then you have to look at whether you're actually exposed to it. And then in order to do that, people also look at like a life cycle assessment to see, you know, where chemicals are released over the entire life cycle of the chemicals manufacture, use, and disposal. Whereas, but today I'm just talking about the first point, which is comparative chemical hazard assessment, which is basically, okay, we're just going to look at the different toxicity values and hazards for the chemicals we're looking at. We're not looking at exposure, and we're not looking at the life cycle assessment. Although in the future we can add exposure. And I think one of the things that we are working on now is to actually add an extra column in our output that gives it like a qualitative indication of how much exposure we get. So it's based on a model. So we can incorporate a little bit of exposure into our output for our our hazard assessment tool. So the hazard comparison dashboard. That's animated. Okay, so the purpose of the hazard comparison dashboard was that an OECD review identified there's gaps when we're trying to compare chemicals in terms of hazard, in that it's really hard to gather all the different data that you need to compare chemicals over many different hazards. So we came up with the hazard comparison dashboard, which would basically use a lot of automation to compile a lot of data from the literature and websites and all that, create a giant database, and then when the user just searches for a chemical, you can populate a table and get all the different experimental values, GHS scores, Qscr predictions, and put it all in one place, and then just be able to get all that data just with a single click once you've searched for the chemical. So that's the goal of this, is to automate the whole process of compiling all that hazard data and then display it in a nice color-coded format so you can kind of immediately see which are the hazards of concern. The hazard comparison dashboard basically gives you scores in terms of low, medium, high, very high for a series of different hazards. There's human health hazards such as acute mammalian toxicity, carcinogenicity, mutagenicity, and so on. There's ecotoxicity in terms of acute aquatic toxicity, chronic aquatic toxicity, and then it gives an indication of fate in terms of persistence and bioaccumulation. Several of these toxicity value or hazard categories have asterisks. These are ones that we currently have Qscr models to predict, different toxicity values for these hazards. So that's kind of handy. And in the future, we want to add more models to be able to fill in more data gaps, because it's very hard to get data for all these different hazard categories for the chemicals that you care about. To compile the underlying database for the hazard comparison dashboard, there was a large amount of work that went on to pull data from many different sources. I pulled data from GHS hazard codes from places like Australia, Canada, ECA, Japan, Malaysia. So these are basically, scores like H301, H300, like a certain code that tells you how hazardous a chemical is in different categories. I pulled data from hazard categories such as Germany's Permanent Senate Commission for the investigation of health hazards, chemicals, and the work environment. These are just the MAT Commission, basically. And New Zealand's EPA also compiled like hazard categories for these categories. I also pulled in quantitative toxicity data from sources such as Chemity Plus, and then EPA's ToxVal version 8, which is a very large database of toxicity values, which has things like NOELs, LOELs, LD50s, LC50s. It's a big database. So adding ToxVal really helps in terms of filling in data gaps and actually giving quantitative toxicity values that a lot of risk assessors want to see, because like sometimes things like hazard codes, you don't always get to see what the actual quantitative toxicity value is. If something is H300, you may want to know, well, what exactly was the LD50 value? But if you pull data from something like ToxVal or Chemity Plus, you actually see the quantitative numbers for these, and sometimes that's what people care about. They don't necessarily care about what code it is; they want to see the number. So that's the advantage of these. And again, the tool actually pulls in Qscr predictions, and we can also predict them in real time. So if we enter a chemical that's like a brand new chemical that somebody came up with, you could have a predicted value. We integrated a web test into the hazard comparison dashboard to predict some of these properties. We're going to integrate opera predictions. Opera is useful for predicting things like endocrine activity. And we also integrated Qscr predictions from Denmark. So we have a series of different Qscr models, and that helps to fill in a lot of these data gaps. There's also data from hazardous chemical lists, and I'm not going to read them off, but there's a whole bunch of chemical lists that can basically give you qualitative indications of these different hazards. Just to show you how we basically aggregate data from all these different data sources, is we have to convert them all to a consistent scale. So we have to convert them all into low to very high scores. So if you're looking at, say, acute mammalian tox, you could use quantitative milligram kilogram values for the oral rad LD50 to come up with a score. You could use hazard codes, like if you had H300, it would be very high. And when you have categories like acute tox 2, it'll give you a very high, and some different lists, like all it says is whether or not it's acute toxin. So you can basically convert all these to the same scale, so that when you display the results, you can immediately see, which are the most important hazard categories, and then where your areas of concern are. To come up with the final score for a chemical for each of the different hazards, we use what's called the trumping method. So basically what you do is you take the most toxic score from the most authoritative source. There's 3 different authority levels. The first being authoritative, things like ECA CLP values, or several other EPA sources. There's screening values, such as the raw experimental values from Chem Plus. And then finally, there's the least trusted, which is the predicted values, such as from web test. So basically, if you have an authoritative value, you use it and you just take the most toxic one. But if you don't have an authoritative value, then you drop down to the screening ones and then take the most toxic of that. And then again, you drop down to predicted if you don't have either of the first 2. Just to show you that this is some of the results we had in terms of data coverage. Some of these numbers have changed once we added in ToxVal, but you can see that in certain categories, we have, for the TSCA inventory of chemicals, there's about 19,000 chemicals. For acute mammalian tox, we had 19% of the chemicals had values, and in some of these others, there's a lot less coverage because there's not a lot of data for, say, neurotox, for example, because it requires, any of these repeat exposure ones, they're like long-term studies, and it takes millions of dollars just to run one chemical in some of these repeat pre-exposure studies. So in some of these, there just isn't that much coverage. But that's why in the future we want to add more Qscr models, more experimental data. And it's kind of always a work in progress to try to fill these gaps in. To show you what the hazard comparison dashboard looks like, this is a proof of concept tool that we have. This is on the contractor's website. We don't currently have it available for everyone to use, but this is something that, in the future we'll get this deployed such that it'll be a publicly accessible website, and then we can share that once it's actually made live. It should be coming in the very near future, but we're working on getting it deployed through Amazon. But this is what it looks like. You can search for your chemicals. I've already populated the web browser with like the chemicals that have the most data for them. So it displays them as a series of chemical structures. Then you click on the little cart button and it'll generate the hazard comparison report. So if you do that, you get a series of low through very high scores. And then the more red it is, the more hazardous or something, or more of concern. So these are the chemicals that have the most data, but you can see, so you can immediately see which are the most concerning things. Like for trichloroethylene, for example, it's carcinogenic. It's chronically toxic in terms of aquatic toxicity and just like that. So you can immediately see which are the most things of concern. And if a chemical had a lot of lows, then it'd be a little more benign and might be a better alternative. But the goal is this slide is to show you kind of what data you can get, and you can see it in a single screen. So there's a lot of information on here. You can take this and you can export it to a spreadsheet, and you can get all the different underlying records that were used to assign these scores. Another neat thing about the tool that we're developing is that we can tie into EPA's chemical transformation simulator, which is a tool that generates breakdown products via environmental and transformation pathways. So if you had, a chemical such as triphenyl phosphate, and then you turned on the CTS chemical transformation simulator for 4 breakdown generations, it'll take triphenyl phosphate and it'll tell you that there's 2 likely breakdown products, diphenyl phosphate and phenol, and then you can look at the hazard scores that you get for the breakdown products. So it's kind of cool to see because like for example, triphenyl phosphate has a lot of low scores for these hazard categories, but if it breaks down into phenol, you get a lot of highs. So in some cases, you may be concerned about, okay, well, what do we, does this chemical break down into something more toxic in, say, a body of water, for example? So you might want to know, how hazardous the breakdown products would be. So that's kind of a cool integration into it. Another thing that you can do is if you wanted to, if we had a lot of data gaps for a chemical, you could click on this second drop-down box and change it to similar, and then it'll give you similar chemicals in the database that are similar to the chemical we're looking at. So if you're looking at triphenyl phosphate, you can see that it gives you these other similar chemicals, and then it gives you the available data for those. So it just quickly gives you, it lets you do some sort of analog searching, so you can try to fill gaps. I mean, it's not a great example because triphenyl phosphate has a lot of the data gaps. There's not that many data gaps, but in some cases, you'll have a chemical with very few categories filled in, and then this analog searching becomes a lot more important. Just to show you, in the downloadable version of test, you can do something very similar. So you could search for the chemicals that I showed you in a few slides ago for the hazard comparison dashboard in the batch mode of test. So you search for that, it populates a batch, and then you click on this hazard comparison button, and it'll give you the same results that I showed you from the web browser-based version. It's just that this is in the downloadable Java application. So it's basically the same output. And then it's kind of cool because let me go back. If you click on one of the cells in here, you can immediately see the score records that were used to assign the final score. So for this chemical, the most authoritative source is that first row, and the highest score, of course, there's only one record, so you take this high value. So if you went back to this other chemical, you'd see that the system, it was a high here, but that's what this row gave you. So, and then you can take all this data and export it to Excel as well, just like you can in the web browser version. Now I'd like to outline some strengths and limitations of the hazard comparison dashboard. The strength is that you can rapidly compare chemicals and retrieve hazard data. It takes a lot of work if you actually had to pull all this data for yourself from the literature, because you'd have to search one by one all those different sources. So it puts it all together in one spot. It automates the whole process of running Qscr models to fill data gaps. There still is some limitations that, you're still going to get some data gaps. You might be able to fill a data gap if you went into the open literature and then read some journal articles, but it's not really possible for us to pull in all the data from all the journal articles out there. But so there's going to be data gaps that the only way you can fill is if you actually did a very detailed one-by-one chemical thing. But we do a pretty good job of getting the low-hanging fruit and combining all the different data that's available. So, and there's also some limitations that, you don't always know all the details about an experimental value in a database. So, there could be some QA issues every now and again, because it's sometimes when you try to aggregate, hundreds of thousands of toxicity values, you don't always know for 100% fact that it's the right toxicity test that you're looking for. And the only way you can really do that is if you go back to the original study and read all the details yourself, and then make absolutely certain it's the test that you think it is. But in most cases, we're pretty on the money in determining, okay, this was a NOEL value for systemic toxicity, or this is a NOEL value for neurotoxicity. But the only way to really know for 100% sure is to go back to the original source. So we can't fully curate every record when we have hundreds of thousands of records, but we can compile them all, then give you the URL, and you can look it up and double check it if you really, if you want to make 100% sure that the data point is what we think it is. So, but anyway, so we've tried to just automate this as much as possible, and then if people need to double check, they can do that. Future needs, we need to update all of our data sources. Obviously, when you pull in data from many different data sources, things are going to change over time, so we have to update those. We want to add more QSA models for different hazard endpoints. We want to pull in things like quantitative data from REACH dossiers and things like that. So we want to keep working on populating the database so that when we display our results, there's not going to be a lot of empty boxes. So, and with that, I'd like to ask if anybody has any questions.
There is a couple questions in the chat, and Anthony linked to your article, developing the methods for this alternatives assessment, database, this comparative database. But do you know, off the top of your hand, there's other similar hazard comparative databases out there like Pharos, which was developed by the Healthy Building Network. Do you know if you compared the methods that they use versus what you're using, and how do they relate to one another?
They're fairly similar. I mean, we have most of the same data sources. I mean, I think theirs is a like if you want to get full access to theirs, it's not free. You have to have a paid membership. And we also have Qscr methods that are built into ours to fill in data gaps. So it's a similar in concept, except that we have pretty much most of the same data sources. Then we maybe have some that they don't have, and then we also have Qscr methods. So.
A question from Andrew Rubin. He asks if the hazard comparison dashboard incorporates data from pesticide or from registered sources such as pesticide registrants that are noting active ingredients.
I'm not sure. I mean, let me see here. Go back. I mean, because these are the main data sources, and we have GHS data, we have different hazard categories, quantitative tox data, different hazard chemical lists. I don't think we pulled data specifically from pesticide data sources with active ingredients. I mean, but the software does, list all the different data sources. So, and then the paper that Tony listed will have all the sources as well. Was there any other questions or?
Not in the chat, but any other questions that people would like to explore with Todd here? And thank you, Anthony, for all your helpful links that you're giving our audience. Just kudos to you is what we're getting, Todd.
Okay, I can live with that.
You're getting amazings.
Which is great. This used to take us days and days and hours to do, and we were always paranoid. Are we missing something? And is it current? And this just makes it so much easier. And then to weigh both human health and environmental endpoints. I mean, and physical hazards too. It's quite impressive. Oh, yeah. Look, you even gotten agreed from Lauren Hine. Wow. The mother of all hazard tables and A4 program committee co-chair. This is just great. All right, if there are no other questions.
So Topher's asking the question when this will be available, and we will cover later on the future work section, which will include the updates that are coming and potential timelines. Everything with COVID is tentative, I'm afraid.
So is this tool currently available, or it's about to be released?
Go ahead, Tom.
No, I was just going to say it's about to be released. I mean, we have a version that we have on our contractor's website, but we don't really want to give that out. But yeah, I think in the very near future, like what would you say, Tony? Like within the next month or so?
Yeah, so we're in the process of pushing this out to Amazon for hosting. Then it will go through a security scan on their side. So it will be the first time we've ever pushed a site like this, but we're hoping somewhere between 4 to 6 weeks.
Wow.
And one of the primary reasons we don't want to push you at the contractor's website is it's always changing. So he can be doing updates every 24 hours of new capabilities, functionality, etc. And we don't want anybody to be disappointed with stability. In terms of the question that was asked about pesticide active ingredients, so the HCD has a comparison dashboard that you see is based on data that were grabbed in March of 2021. We have relationships in place so that as new data are added into databases across the agency, we get monthly updates of what those chemicals are that go in those various databases. So Substance Registry Service, as an example, we work with pesticides, we work with, if we are missing those chemicals, everything starts really with the DSS Tox database that underpins the dashboard. We register every chemical there, we make sure we have the right structures, then ultimately from there, it has to find its way out to other tools. So even though internally right now, our internal dashboard that Todd and myself and Catherine can access and all of our colleagues inside the firewall is 1.2 million, you will only get access to the 904,000. But overnight, that number of chemicals changes. So we do releases on this cycle, and every release we do, we have to figure out how to get those new data under the tools. So the hazard comparison dashboard is a proof of concept and already out of date in terms of data.
There's just one last question here from Jennifer Tenier, who asks if it's possible to change the order of some of the columns to align with some other methodologies of comparing hazards.
So you have the ability in the tool to create a custom view of the data. So what Todd showed you is the full view. We have two specific workflows already added into the tool, one called site-specific screening, one called emergency response. Those are pre-configured based on consultation with certain groups internally, but you can create your own custom profile. So you can't change the order per se, but you can change what you view and don't view. So if you just wanted 3 columns, you could build that in a custom profile. And that is your profile view. It doesn't belong to anybody else.
Great. I'm not seeing any additional questions.
No, I think we all want this under our Christmas tree in what, 6 weeks or something. So
that's why it looks like Christmas lights. That's why there's so much color.
You've all been hopefully very good all year, so we don't want a lump of coal. We want HCD. So this is a real game changer. This is wonderful. Any final questions? If not, we will take a 15-minute break. Looks like we're actually back on time again. And
thank you, Todd.
Right. Let's reconvene at 1:20, and we'll hear from Catherine and learn about exposure data and models next. Thank you.
All right, fantastic. All right. Well, thank you everyone for tuning in and joining us in this last, what I would call a really information section. We'll move on to future work and things we're planning on the pipeline next. Thanks also to Molly and Meg for pulling this together and others. And thanks to Tony and Todd for giving me a great introduction so I don't have to spend too much time going over technical details. They've really done a great job of covering the dashboard and the general framework of Qscr modeling, so I don't have to. I'm really going to dive more into the exposure data that's available through the Computational dashboard. And just as a quick disclaimer, we always have to do this. These are the views of the authors you're hearing here, not necessarily the views policies of the EPA. And also before I get started, because I worry I'll run out of time if I don't, I am here representing a whole host of people who have just done amazing, fabulous work that really has made what you're about to see possible. I just want to go ahead and acknowledge both the people within the EPA who work on our exposure forecasting or ExpoCast project, as well as collaborators we have across other universities, other research institutes, and government organizations as well. So as an outline of my talk, I'm going to give you a little bit of background and motivation of where we're coming from in terms of exposure science and wanting exposure estimates that kind of forms the rationale for the source of data we've collected and the source of information we have. And how we plan to use those, but how also you could think of alternative assessment as kind of analogous to what we're trying to do with our exposure data, and hopefully give you some context for how you could use this information in your daily work. I'm going to talk about the different types of data we have within the dashboard that we surface. I like to think of these in 3 different types of categories. There's collected, which is we just pull from another website or another data source and we make available to you. There's assigned data, which is, I tend to think of it in terms of like metadata. There's some extra piece of information from that collected data that we can append to it to kind of give you a better picture or a better way to use the data. And then there's also predicted data. So this is where we've used that collected or assigned data, we've built a model, we've verified the model, and then we're making some prediction based on it that also can help inform some decisions. I'll spend the second half of the presentation really talking about how to get at this information. Tony did a great job at the beginning, kind of getting you acquainted with the layout of the dashboard and pointing to where everything is. I'll just dive in a little bit more detail in this. Let me get my pointer going into this exposure tab that you saw on the detail page and kind of go a little bit more through each of these subtabs there. So the research project I work with at EPA is really the Rapid Exposure and Dosimetry project. And what this means is, and what our focus really is if you think about it, we've got hundreds of thousands of chemicals. We've got in commerce that we come into contact with on a daily basis. They're in our clothes, they're in our, the cleaners we use around our house, they're in our cars, they're in the foods we eat, whether we know they're there or not. And really and truly what we're trying to do with this project is say, which ones of these should we really be concerned about? And if we are concerned about them, which ones should we maybe focus on phasing out? Which ones should we try and replace? And so on and so forth, kind of just getting an idea of, of this massive quantity of chemicals, which ones should we really be concerned about? The approach we take is really looking at both hazard and exposure. For us, with our hundreds of thousands of chemicals, if something's really, really toxic, but the vast majority of the population is never really exposed to it, it falls down to something we care a little bit less about, right? Because it's not something that the general population or any highly exposed population really comes into contact with that much. Whereas when you get to the more medium and high risk, we maybe have a greater concern for those, something that may be a little bit more hazardous, but the large portion of the general population is exposed to really would pique our interest. Whereas if something's, slightly less, hazardous and slightly less of the population is exposed to it, it's still of greater importance to us and something that the general population never really sees. The next question that follows then is, how do you get at both these exposure profiles and these toxicity profiles? Well, toxicity we've kind of seen a little bit of today, both through Todd and Tony's talks. We have these high throughput toxicity assays through the Tox 21 consortium, through our ToxCast program at EPA. We can run, fairly rapidly, lots of chemicals through many different assays and get some sort of information about toxicity there or bioactivity there. But really and truly, the high throughput exposure is the trickier part to that, but it's needed for this sort of prioritization or evaluation. And we do that primarily through our high throughput exposure models. You see an outline of our SHEDS high throughput model up here at the top, kind of the workflow for that. And it really is it has several moving pieces. It has several different types of inputs you need. And it really is a challenging question to get all of that information just to feed those exposure models to get these sorts of estimates to help us prioritize the chemical. So that's really what I want you to see as where we're coming from when we collect our exposure data is we're trying to feed these high throughput exposure models so we can assess hundreds of thousands of chemicals and make a call on which one should we probably focus more of our attention on.
Catherine, quick interruption.
Yeah.
What
Sure.
we have a request. There's a bar that's appearing on your screen.
I didn't know others could see that. Yep.
Yeah,
Let me hide that for y'all.
Perfect. Thank you so much.
Yeah,
There
no
you go.
problem. Thanks for letting me know.
Awesome.
I appreciate that.
Okay.
I never know what's just mine and what everybody else is forced to see too. So yeah, so those exposure models really require a lot of information to like actually make those estimates. And what's even more challenging there is the data that's required is not always available to us. And maybe it's a little bit out of order here, but you'll see in a second, some of the things we need are information on users, like how do users use, consumer products or other products in their day-to-day life. We need information on how much how much of a certain chemical does someone come into contact with. And if you think about the whole manufacturing chain and how you get all the way down to the receptors of a human or to the ecological flora and fauna, there's a lot of data that really goes from how do and even one step above these industrial, the raw materials, how do you go from quantifying the amount of chemicals in a raw material that actually gets through to a human? And this whole web of information, as it gets processed through the consumer goods, as it gets processed through the different industries, and then goes through different media to actually interact and be, a source of exposure for our receptors. And it's not just, getting at all this information, it's getting at it for different populations. We consider consumer to be a more general population. Everyone should be a consumer of goods in a general population. And therefore, they have these certain streams of exposure. But if you're someone who works at a foundry, say, or at a chemical manufacturing plant, you have occupational exposures that are very different from the general population as well, and so we need to consider those. And not only that, but you also have these ambient exposures as well that just come from your day-to-day contact with different media in your environment or your life. And so that doesn't even touch on the ecological flora and fauna. And so, when you look at all this and you think about it, it really would be impossible to think of one single high throughput exposure model that could account for every single type of exposure, for every single type of person, for every single type of chemical, let alone getting data that really makes that estimate really well known. There we go. So to address this problem, we've really taken an approach to exposure modeling that is consensus exposure predictions. And Todd talked a little bit about this with some of his work with Qscr modeling. But all a consensus model really is you're taking a bunch of different models. Excuse me, and I'm sorry, I'm recovering from a cold too, so I'll try to mute myself when I have to cough. But apologies if I make loud noises into the microphone. A consensus model really is just taking a bunch of predictions from different models and seeing where the general trend of all of those models lie. So you can think of this in terms of a couple of different examples I've put on the slide here, right? When you're predicting the path of a hurricane, you see like one trend going on, the Weatherman's map or the NOAA map or something like that, but that really isn't just the one hurricane model they have. There are many different hurricane models. And what you see on those maps are generally the trend of the majority of those models that have been, you've made a consensus prediction as to where that route will go. We're seeing similar things being done with COVID-19 caseloads, right? So we have surveillance data that allows us to feed models. We have many different models that we can make a forecast on and say, oh, okay, yeah, our models are kind of matching the trends we currently see. And then we can make predictions based on those accurate models. And then we can see where they all tend to converge with when we think the caseloads will begin to drop, given the data we have now. And we can kind of estimate when we think certain peaks in COVID will fall and stuff like that. We're doing the exact same thing with our systematic empirical evaluations of models, the SEAM approach, with our exposure data. We have measured data from the National Health and Nutrition Examination Survey, NHANES, where we have concentrations of chemicals that have been measured in American serum as well as American urine samples. We can take those concentrations that are measured, infer an exposed dose from them, and then compare that inferred exposure to model predictions from various high throughput exposure models. And then we can do a joint regression to kind of minimize that uncertainty and calibrate our models to know which models actually do a better job of predicting which chemicals and make an assessment from there as to what may be a better prediction. And as I alluded to earlier, feeding those high throughput models is not easy. We have stuff that we call habits and practice data, where we need to know information about the users themselves. What products do they use? How much do they use them, at one given time? How frequently do they use them? What activities do they do that may put them in contact with certain, articles in the home, durable or non-durable goods in the home? What kind of food do they eat? That can determine whether or not there's been food contact materials that leaked into the food, and so on and so forth. And then you have issue of what's in the products themselves. Are there compounds intentionally added? Do we know how much of that has been added? Do we have information on unintentionally added compounds that may come through the supply chain? As something sitting on a shelf for some time, you have the potential that ingredients within that product could react or degrade and have other products in there. You could also have leaching from the packaged material themselves. And then knowing what types of exposure may, occur depends on information of the chemical itself, right? Like physicochemical properties. If something's volatile at room temperature, you're likely exposed to it through inhalation and possibly dermal as well. Whereas if it's, a liquid or a solid, there's typically only dermal exposure. So these are all, very important pieces of information, but the issue is that data is not nice and neat in any one location. And sometimes it's not even in a form that you would really expect it. Nobody just kind of hands it over on a silver platter. So we've made a lot of efforts over the last almost a decade of really going out and finding data where it may not be publicly, or where it is publicly available, but it may not be in the form we're expecting it to be. And then working with folks with the dashboard to actually get that data out to the public. So let's go ahead and talk about collected exposure. So these you can think of in terms of a product use categories, chemical weight fractions, and chemical functional use. And the way we surface, Tony earlier was talking about DSS Tox being the chemical database that really is really surfaced through the dashboard and really provides a lot of the information about chemicals and their properties through the dashboard. A lot of the exposure data you see shown through the dashboard is surfaced through the Chemical and Products Database, or CPDAP. And this database really is a combination of, almost a decade's worth of effort to collect exposure-related data so that we can build better exposure models, just for this point of, prioritizing chemicals in terms of exposure. So one of our first efforts was the CPCPDB. This is the Consumer Product Chemical Profiling Database. So this was an effort to go out to a major US retailer, collect all the MSDS sheets they had publicly available for any consumer product they had on their website. And it really was our first chance to go out and say, a MSDS sheet, a material safety data sheet, or an SDS safety data sheet, provide information on the chemicals that are in a consumer product and some range, typically of quantity of that chemical in the product. Now, there's caveats to this in that a manufacturer really and truly only has to list product or chemicals that they know are in the product that potentially present a hazard to consumers. Some manufacturers stick strict to that line. It's only if they know that there is a hazard associated with that chemical do they provide information on it. Some are, leaning towards, more openness in their products, and they'll list every single product they know they've intentionally added. They also have that range of weight fraction of the product, and that, is also challenging because sometimes you'll see a chemical have anything from a range of 10% to 90%. And so that could be anything, really. But that really was our best chance at getting information on material and consumer, or how much of chemicals are in consumer products. We also have the CPCAT database, which was a broad categorization of chemicals. So we had also found that use was extremely important. I think this was alluded to in one of the questions earlier by the audience. Use is extremely important. Knowing whether something comes from a therapeutic background, or whether it's from an industrial background, or whether it's used in food. These are really useful pieces of information that can help you decide where you're likely to be exposed to a chemical at. And so that's really what CPCAT provided us. But since we've realized how useful these two databases are, we went out and collected, made other efforts to collect other pieces of information. We have information on more SDS sheets on ingredient lists of consumer products. So this is, if you think about some cleaning materials and some personal care, and all personal care products in the US have to be listed in weight fraction order, right? The first ingredient on the list has the most quantity in that, particular product, and then it goes on down the line in decreasing weight fraction order. And so we were actually able to build a small model that we could use to estimate weight fractions based on that ranking. And we've provided that information in CPDAT. Not only that, we have functional use data, which was also asked about earlier. So this is, why is a chemical added to a particular product? What purpose or what function does it serve in those products? And so we have information about that in CPDAT. We also have measured data from non-targeted and suspect screening analyses. So in these situations, we went and collected actual consumer products or articles, took them in the lab and analyzed samples to see what sorts of chemicals we could identify in those products. And we make that data available through CPDAT as well on the dashboard. And like I said, we make it available through the dashboard. So just as a little bit of reiteration, we have broad chemical categories. We have, pretty general or pretty well-defined chemical products or roles of chemicals and products. We have information about weight fraction, as well as chemicals that we've identified. And we make all this publicly available through the dashboard. But if you were paying attention to some of those dates that, those efforts started, 2013, 2014, stuff like that. But CPDAT is very much dynamic. It's not something we've just built and we've left alone. It's actually gotten so large that we've had to build our own internal application, which we call Factotum, which helps us store and manage and curate this sort of exposure factor data. This was a snapshot I took as of Friday. So you can see we have quite a bit of information on different products, on different chemical records, and different products that are linked to what I'll talk about in a minute as product use categories. This is a really nice application we've built that really allows us to take, any one link where we found data and go through the whole workflow as to here's the link, here's the script we use to pull the data, here's how that data was actually pulled and put into our database, and here's the opportunity if we notice any errors with that data to go in and correct it and push that information immediately to CPDAT. It also allows really amazing search mechanisms to go through and actually look for, if we're on the dashboard and we notice that something is labeled, let's say as like a flame retardant, Tony will remember this, as a flame retardant that shouldn't be, we can go through and we can find exactly what piece of paper from what website allowed us to make that call within a matter of minutes. So it really has become a great tool for us when we're curating this exposure data to make sure that we're delivering the cleanest, best version of our data to the public and most accurate version to the public. Unfortunately, this is currently just a tool that we have internal to EPA. So if you have an EPA.gov, email address, you can get access, or if you're behind the firewall, you can get access to this tool. But in our next research planning cycle, we hope to, build in the ability to make this a external access feature for the public. So hopefully in a few years, we can come back and talk to y'all about that as well. There's a couple of other pieces of collected data on the dashboard that I'm not particularly going to go into too much detail with today, just because there's other data I've got to get to. Two of these are other pieces of data that are released by a sister office or not a sister office, by another office within EPA. That's the Toxic Release Inventory, TRI, fact sheets, as well as the production volumes from EPA's Chemical Data Reporting, CDR. These each have their own websites. They have, data sources and stuff like that that we pull in at intervals onto the dashboard. So there's information about them as well. So as I said, I won't spend too much time with them. The other thing you'll see are the inferred exposure doses from NHANES. So this is those, inferred exposure doses that I talked about earlier that we'll use with theme. The only thing I'll talk about them here is they're really and truly only for about 106 chemicals. So you're not going to see a lot of chemicals on the dashboard that have this sort of information. And it's really limited because there's only so much of this measuring that you can do in any one NHANES cycle. They're limited by the number of chemicals they can cover, which really limits our monitoring data. We have efforts underway where we're planning on expanding that to as much as we can. But don't be surprised if the majority of chemicals you look for on the dashboard don't have NHANES data, unless you're just looking at NHANES chemicals. So that wraps up collected. Let's go on and talk about assigned. So we have, all of this information about different products in the dashboard, right? We have MSDS sheets, we have ingredients lists, we have functional uses. But at the end of the day, when you're looking at an exposure model, typically, I'm not going to say always, but typically, you really don't care about seeing how much of chemical Y is in brand X of oven cleaner. That's not something you typically do with these high throughput exposure models. What you typically care about is which chemicals are you exposed to in an oven cleaner. And so for that reason, we really had to find a way to categorize all of the products we have in CPDAT. And we did this with our product use categories, or PUCs. There are several other groups out there that have their own product categorizations, and there are crosswalks between our PUCs and each of those categories. For example, I think we have like crosswalks to reach categories and a few other types of categories out there. Excuse me, and you'll find those in the publication below. These PUCs are hierarchical, so they allow you to, look at across different levels. And so you'll see that in the example I give over here. This is a snapshot from our factotum application that I mentioned earlier. So these are our formulation PUCs. These are PUCs for chemicals or for products that you consume on a regular basis and go out and buy again. We have general categories of them that you can see here, and we're color coded by the quantities currently within factotum below. So you have things like cleaning products and household care. And, you can have things like landscape and yard, you can have things like pesticides, all these sorts of things for formulation PUCs. Now, what I'm not showing are other things we also have added in since we originally created CPDAT, which are articles. We've had a lot of collaboration to collect health product declarations for building materials. And we have, so those go under an article or a durable goods sort of PUC, where there's something that would have a different type of exposure because they're kind of in the house long term. We have industrial PUCs now too for, we're gearing up and looking towards occupational exposure in the future. So we have things that, the general population wouldn't necessarily come into contact with, but are used in industry. So, this is just, a small snapshot that you're seeing here. The other nice things about these PUCs is they, especially in terms of exposure modeling, they allow us to look at attributes which are important for the models themselves. An example is sunscreen, right? If you're looking at sunscreen, there are different types and different formulations of sunscreen available. You can have something come out as a cream, you can have something come out as a spray. You can have different types of people you're targeting when you're doing that, right? Like, is it just regular sunscreen? Is it sunscreen safe for children? Is it sunscreen safe for babies? And so we have these different attributes that allow you to consider all of these things. One of the other ones is a 1 or 2 component products. So sometimes when you're going down the aisle, you'll see these gift basket sets of like nail care kits or like spa gifts and stuff like that, or different car cleaning kits and stuff like that. And so that allows us to kind of handle the different components that may be in those sorts of kits as well. And then the last type of data I'll talk about are the predicted data. So this is both chemical, this gets back to the chemical functional use. So we've collected that data, but we also use it to make predictions. And then all of the other data I've talked about really goes into feeding some of our exposure predictions as well. So I talked about consensus, or I alluded to consensus exposure models earlier with the systematic empirical evaluation of models, so SEAM. In our latest rendition of SEAM, we really use not only the exposure models that I've described, but we consider the pathway of exposure to decide which models we really should be using to predict which chemicals. So in this situation, we take a chemical structure and we feed it through what we would call a pathway prediction model. And that shows you the 4 pathways we would consider. And it's really a yes or no question. Does this chemical structure match other chemicals and that would have this sort of pathway, right? So if you feed a chemical through, you would get some sort of probability that says yes or no, this chemical is a resident or should have residential exposure, or is likely to have residential exposure, and so on and so forth. If all of these pathways are no, then it goes into an unknown pathway, one that we can't really build a model for, that we don't know that we have a model for. And then depending on the different pathways it has, it goes into different predictors towards the end. These are different types of exposure, high throughput exposure models we have that were part of this effort from many different institutions to build the SEAM3 model. And so the output you get from that are really intake rates across more than 400,000 chemicals, right? So on that previous slide, if we were to, when we input like all of the chemicals we had structure for, all the chemicals we had data for, about 30% of those fell into that unknown pathway that I talked about. And we considered those to be outside the domain of applicability of our models, right? We didn't have a model that we knew could account for it. But when we did have chemicals that were in at least one of those pathways, we were able to say that the median intake rate was below, 1 mg per kg per day for about 474,000 of those chemicals. And that's to say that this 95% interval doesn't necessarily reflect the most highly exposed, but it's the median estimate, right? So this is for our general population. And so those are the sorts of, and I'll show it in a little bit, but those are the sorts of exposure estimates you'll see in the dashboard. And then on top of that, we took the functional use data for the chemicals that we had collected information for. We actually realized we didn't have a lot of use information for the majority of chemicals in the dashboard. So we decided to build a model that would fill in those gaps for us. So these are the quantitative structure use relationship models, Qsrs, you'll hear them come up. And this does exactly, or not exactly, but a similar thing to what those pathway predictor models do for exposure. You take a chemical structure, you feed it through a suite of models, and you get a yes/no prediction for each one of these functional uses. And so the functional uses you see here that have X, they weren't valid models, so we don't predict with them. If they're green, we predict with them. So you would get some sort of prediction out of all these structures to say, these chemicals are likely catalysts, these are likely cross-linkers, these are likely colorants. And you can do this for any chemical where you have a structure for it. We've actually found a lot of use with these Qscr models. Early in the day when we were first developing them, we found that we could actually use functional use as a predictor of weight fraction in chemicals. This was before we had made that huge effort in collecting ingredient lists and some more of the MSDS sheets. And so we were using this as a way to fill the knowledge gap between weight fraction. And so we could use these predicted weight fractions based on product type and based on functional use to feed our SHEDS high throughput model and get exposure evaluate or exposure estimates from there. We were also able to use our Qscr models to predict candidate alternatives. So we took the Tox21 assay information. For every chemical that had a structure in Tox21, we predicted any of the functional uses we were able to for it. And then we took that bioactivity information and we said, well, we know these chemicals in Tox21 we have reported information that says these chemicals serve this functional role. Can we look at any of the predicted chemicals and say they have a lower bioactivity, but could also serve that same functional role? And so using that sort of information, we were able to predict candidate alternatives that could potentially serve the same functional use, but also had lower bioactivities. And we proposed this as a method of screening large libraries of chemicals as candidate alternatives. We've also used these models to bolster suspect screening identification measurements. So I alluded to earlier, we have measured data in CPDAT, where we've gone out and performed these sorts of analyses on different types of consumer products and things like that. But you often get tentative identifications. You're not necessarily confirming them. You just, you think they're there and you need to do follow-up study. But how do you prioritize which of those you really need to do that follow-up study with? And we decided to do that based on functional uses, right? If you see a chemical that's tentative, but it's a surfactant and it's in, Windex or something like that, you can say, well, it makes sense that you would see a surfactant there. Let's go ahead and say that that has a higher likelihood of being in this sort of cleaner than a chemical that's not serving that functional role. So that really does cover most of the data that is of interest in the dashboard. I haven't heard any interruption from Molly or anyone else, so I'm assuming there's no questions, or if there is, now may be a good stopping point.
Tony's posting a bunch of great links to papers that underline a lot of what you're presenting. But maybe you could just further expand on one of the questions from Topher Beck, who asked if related to product use categories, can you search chemicals by functional use independent of the product type? For example, chemicals that are used as anti-ozonants in rubber, regardless of whether it was used in a household product or a building product or a vehicle product. So do you have to
that's a
search
great
by
question.
product type?
So that is currently not a functionality that is available on the dashboard. What I will say is because the dashboard, as Tony talked about earlier, was really meant to handle, chemicals, providing information about chemicals. The factotum application that I said we were working on and that we really hope to make public really should be more exposure-based, right? So it would handle those sorts of queries where I want to look at all chemicals that are known to be solvents or something like that, right? And the quickest fix we could think to do stuff like that in the dashboard now, and Tony can jump in and correct me if I'm wrong, is really to make a list of them in the dashboard, as he showed earlier. But we're hoping really to have a more exposure-focused twist on this sort of information be publicly available in the future. All right. If I don't hear anything else,
we've done many lists
Go ahead,
like that. Yeah, many lists like that, Catherine. I'll put some examples in the chat box, but we have no other path other than doing that for right now.
right, exactly. It's just they're very related pieces of information, and they're both both the dashboard and our factotum application deliver, useful information. But it's who's the intended user and what type of data they're really wanting. And so the dashboard just out of necessity has a more chemical focused nature. Whereas, if you really want to get at exposure data and drill down like you were talking about, Topher, you need like a different way of looking at that sort of information. And we're hoping to provide that in the near future. I will also say, and I'll link to it, really quickly, I'll link to it at the end. You can also download the SQL database of CPDAT itself, which would enable you to do those searches on your own. It's probably not the easiest way to get at the data, but it's a way if you wanted to.
Meg asked, and it's also probably more of a comment that you all want to take up in the future section of this short course, but ECA has its substances of concern in articles or in products, the SCIP database, which was actually just recently published. Any future movement about kind of linking to that database within all of this going forward?
Go ahead.
No, I was just going to add on just that it's based on requirements under REACH for users of articles that are using substances of very high concern at 0.1% by weight to actually report those substances within specific products. So again, just kind of getting at where these chemicals live.
Yeah, I know there have been issues in the past in getting a hold and actually publishing REACH sort of data on our own websites, right? Because there's just, technicalities there of, who owns the data and who can do what with it. As far as like incorporating it internal and potentially aggregating it out to the users themselves, that's something, we have capabilities of doing. And we have curators actively working to go out and find new sources of data and bring that in. But it really becomes more of, a technical question on like whether it's something we can actually make available or not based on legal terms.
Great. And maybe just if we have the time, there's an interest to kind of explore specifically how the lists look with regard to flame retardants. And I know Tony's kind of put some details into the chat, but maybe if we have time at the end, at the end of this to kind of explore what some of this might look like for products containing flame retardants.
Yeah, sure. Let me do a quick walkthrough of just an example chemical and how we can go about that, and then we can either cover that in the next section, or either I can do my best to attempt a live demo towards the end and show what we have there. So you've probably already seen this at, I don't want to say it nauseam today, but you've seen it a lot today, right? Like hopefully this should be familiar to you. This is the homepage of our Chemicals dashboard. And I am just going to say, I have a really tiny screen and sometimes text is really hard to see. So I'm just going to zoom in a lot on these. So just bear with me as I do that. So this is the search box Tony was showing earlier. And if you want to get at exposure information, he was showing some chemicals. I have just selected BPA because I happen to know it's chemical. We have a lot of information for. you can start, as Tony showed, you can start typing and you get the type ahead. And you can select and click the phenol, which is essentially what I'm going to show now. Here's the landing page that Tony was showing earlier. And when you really want to get at the exposure information, it's over here to the side. For those of us with tiny screens, here you go. And it really pulls down this list that I've been showing the whole time as I go through my outline, right? These are the different pieces of information we have on exposure. Again, for people with tiny screens. And I will say, if sometimes the dashboard takes time to load for me. So if you're having trouble, these are the links of each slide or of each web page that I'm on at any given time. The first one we'll go through are the product and use categories, right? So I talked about CPCAT earlier. That was really our broad categorization terms. Where did we find these? Where did we find some sort of use information at all about any given chemical? But then we also have those product use categories, those pucks I was talking about. You'll see some with blanks, and that's just from, we have some ways that we're trying to auto-assign pucks, and we're trying to curate those pucks. So sometimes you'll see them with a blank. Those are things we'll take care of in the future. And they really should have gone into not yet categorized, but that's just the way it goes sometimes. But you can see here the different sources that list BPA and the different sorts of materials or pucks we have found it in. Further, the nice thing that they've really thought about when putting this in is I had no idea what the CEDI was, SETI, I guess. But if you hover over it, we've got these, hovers or tooltips that will come up and tell you exactly what snippet of information or what that particular puck or CPCAT cassette means and where it came from. So as I said, we have our broad use categories from the CPCAT cassettes, and we have our product use categories. So we're going to move down to the chemical weight fractions. So these are really the MSDSs that I was talking about, the different ingredient lists. We had information from our suspect screening analyses and things like that. And we even have a few health product declarations in there for when we have some sort of building material. And so those are the sorts of things you'll see there. You'll also see where we scrape the information on the minimum and maximum weight fraction. So if the SDS sheet actually does say, this is the range, then we give you the range. If there's only like a single value there, like if it says it's 0.5 or 50%, we put those both the minimum and maximum. We provide the product name, we provide the source, and we also provide the puck if we have it. We also have this nice search box at the top. So if you're looking for something in particular, so in this case, I was looking for the different products that we had identified this chemical in with our suspect screening analysis, you can do that and it'll start to filter the list for you, right? So we've gone from the 246 records you saw here to just the 4 records in the places we identified it. And I bring this one up because, yes, you'll see it. You can kind of highlight here. If we were live, you'd be able to highlight here and it'd tell you about that. But also to pay attention to these sorts of data types when you're looking at these suspect screening data. So we have confirmed chemical identifications, which means we actually went out and we confirmed. So we know to some extent that chemical is in that consumer product. But we also have these tentative chemical and tentative class identifications. And those are the ones where we haven't necessarily confirmed. We think there's a high likelihood it's there, but it's not to be taken the same thing as this chemical is exactly in this product. So just, a small caveat to that sort of data when you're looking at it on the website. We can also move down to functional use information. So what you'll see here is the top table would be harmonized, collected functional use information. So this is like I've been saying all along, we have our collected data. You'll see that you have reported functional use and harmonized functional use, and things are quickly changing. We're working on rebuilding these Qscr models. But what you'll see on the dashboard now is the harmonized functional use, and you could of course hover over it and get the same, information, was really a way based on like modeling constraints and everything like that we had going on at the time. It was really a way to say each chemical that we were modeling or using to build our models could only have one functional use. So if, in this case, we had reported uses of a coupling agent, a crosslinker, a curing agent, and a phenol. Well, instead of building a model for all 4 of those reported functional uses, we harmonized it up to crosslinker, and we said BPA is going to be a crosslinker. And we had an automated system for doing that. So like I said, reported functional use is that, original source functional use, but the harmonized is really something we created ourselves based on all the data we had collected for functional use. But I will say, like I said, we're working on rebuilding these Qscr models. And right around the time we were wrapping up this project originally, OECD actually came out and published a whole set of, harmonized technical functions. And call me lazy or whatever. We didn't go back and relabel each of those and rebuild the models, because also we had modeling constraints that wouldn't allow us to do that at the time. But our future efforts will have everything. Instead of this harmonized functional use that we created, we'll use the OECD's harmonized functional uses. So it should make it more approachable and usable by others.
Catherine,
Now,
quick interruption.
Yep.
A question from Ann Cooper Doherty is, the data that underlie these models, whether you generated them from an SDS or some product ingredient list, is there any way to know when that data was sourced, like the year? I mean, can we assume this always to be kind of active and current, or is this based on an analysis, if you will, that was done 4 years ago? Just again, knowing that kind of product formulations change over time. So is there any way in here to know the year, or if you will, of when this data was sourced for the models?
That is a great question, an absolutely great question. So the information you're seeing right here, right now on the dashboard is from our original publication that was done back in 2016, 2017. So all of that information would be only what we had available at that time. The other bit of information is sometimes with the MSDS sheets, sometimes with the ingredient list or other sorts of data documents we find, they do have a date of when that document was published. And when that's available, we add that to our internal CPDAT dashboard to let us know this was the publication date of this formulation. Other times that information is not available, and we say the day we download it is, that date. We are making efforts now with looking at universal product codes, UPCs, and different barcode sorts of situations to be able to map, the same product, but various formulations of it back, to the same product. That again is something that has a functionality built in the factotum application I was talking about, and not necessarily in the data you would see on the dashboard. So we have it, we're aware of it, we're trying to use it as we go forward, but it's just not something that's quite ready for prime time yet. But in terms of building or updating the Qscrs or the Qscrs, we're actually using whatever information we have, right? We're not really basing it on historical data or current data only. We're just taking, because functional use data can be so sparse sometimes, it's easier just to take what we have and go with it.
Great, thank you.
Yeah. And so if you were to continue scrolling down on that chemical functional use subtab, you would see our predicted probability associated functional uses. And so again, these are those harmonized functional uses that I talked about earlier. Again, in the future, they will be OECD functional uses rather than whatever our data gave us at the time. These, you'll also get the probability that the chemical has each of these functional uses, right? So you can see the different probabilities of bisphenol A having these different functional uses. So one thing to note is I think we had about 44 different Qscrs or different functional uses that we were able to predict information for. But we only took chemicals that were in the domain of applicability of the model and put them on the, so you won't see 44 predictions for every single chemical. You'll only see the predictions that were in domain, regardless of the probability, right? So we're seeing it has a very low probability of being a colorant, but we still give it to you because it's in the domain of that model. Here's that monitoring data. So this is one of the 106 chemicals that Entains actually tracks. So you can see different information broken down by demographic and different, statistical measure or statistical values for those inferred doses. And, this is just showing you zoomed in if you were interested. And then these are the scene 3 exposure predictions as well. You can see we get that 95th percentile, so kind of the certainty that we have in our median prediction, as well as the median prediction itself. So let me also show you how we use this product use categories. Notice we've clicked this rather than the chemicals, but we still have this nice type ahead feature that we've had all along. So if you start typing tests, it'll bring every product category and every use category from, or every product category from, or PUCs from CPDAT and any of those CPCAT use cassettes that we had as well. So you can see the 3 different ones we have there. And so this one, I decided to go with the CPCAT term for pesticides. And so this brings up all 4,300 or 4,537 chemicals that were tagged as having a CPCAT term of pesticides, right? And so it brings up this nice grid below where you can actually go through and look. You can see some have structure, some don't. You can see different bits of information about them below. I believe Tony's pointed out a great deal about all this. But the nice thing here is you also have that ability to send these to batch search. You can decide to hide certain chemicals if you're not interested for them, or you can just direct, if you just want the list of chemical names and their identifiers, you can just download the data immediately rather than sending it to batch search. So that really is a very quick description of how you would go and access the data and stuff like that. I just want to leave you with a quick summary slide that shows, we have this information for, thousands of chemicals and how they're used in different products, how they're used in different sectors, what measured data we have on them. In CPDAT, we make that available through the dashboard, but then we also use that information in CPDAT to add metadata to them to tell you what types of formulations or products they may be in, what types of functional uses we could predict with them, and then as well, what types of exposures you could estimate based on consensus models. So below you'll see again the dashboard link, but then this is also the CPDAT download. So if you're really interested in diving really into the raw data itself, you can go and you can download the latest version. It's a MySQL dump, so get your queries ready. But other than that, thank you very much for your attention. If there's more questions in the chat, I'm happy to take those.
You see it okay?
Looks great.
Okay, great. Right, so I think you've heard from both Catherine and from Todd aspects of their work where there is an intention to rebuild models to make these models available in a future version of the dashboard. This work can be quite time consuming. A little bit about the gathering of data. So for a lot of the test predictions that will be resurfaced in a new version, there's been very significant data gathering efforts gone on for many, many months at this point. Those data get registered, curated, mapped. There are new approaches that are being developed. So you will see the test models come out in the next few months, few maybe many. It just depends on the rate at which we can get the work done and the rate at which we can publish these out. Similar efforts going on from Catherine with the redevelopment of the Fuse models and updating. And you saw the extent of the data that's available in Factotum at this point and how much that's growing. We're always registering new chemicals, as I said. So what you will have seen hopefully this morning, and I'm kind of going to summarize it here, lock it down, then we're just going to answer questions and answers and give you real-time demos of chemicals you're interested in. But what you've seen this morning, hopefully, and now heading into the afternoon, of course, is the power of what we've been able to build over 10 incremental release versions to surface data for close to 900,000 chemicals in the existing version that will be going live. And you've seen that we can come in at a chemical level search, product use category search, and to a certain level, the assay gene searching. Providing access to toxicity data. And if any of you are building your own tools and you want access to these data to include yourself, please do follow up with us. If you are building your own solutions, we have ways to share our data with you and always showing you where you can access some of that. Bioactivity data, of course, continues to enrich version after version, refitting the data, measuring new data, adding new chemicals. The similarity search that is already built into the dashboard, we have already a new version of functionality that has structure search, substructure search, and similarity. It's actually part of the hazard comparison dashboard that we will be releasing in the near future. This similarity search we showed is limited to a 0.8 similarity factor, but we're going to give you the ability to control exactly how you want to use that. Keep changing the thresholds to get a hit set that's of more relevance to you. The read across we touched on gently. The read across module is actually being broken out of the Computational dashboard, so it will be a standalone module. It will still be linked to the dashboard. It will be able to be deployed in your own environment. So if you want to download the code and deploy it locally for you to work on chemicals of your own interests, that will be available to you. And again, still linked up. PubMed Abstract Sifter, quickly talked about this, and we may choose to show that in the time that's left. And this is also available as an Excel add-in, so you can download a version of Abstract Sifter for Excel, and you can not only use this one chemical at a time. If you want to search for 100 chemicals and keep refreshing the available literature on PubMed, you can do that. This was built by our colleague Nancy Baker. She continues to release new updates just every couple of months. She's done some wonderful work there. And the batch search, I hope you can see how beneficial that would be. So you don't have to search one chemical at a time. You can come in with a hybrid mix of names, CAS numbers, NC strings, etc., etc. Now, what's been going on with the hazard comparison dashboard that is not supported here yet in the Computational dashboard is if you have a list of smile strings. So you harvest smiles from any site, PubChem, EBI, OECD. If you have smile strings, then you could take those smiles, put those directly into the hazard comparison dashboard. It converts those smiles into structures that will then go through the test predictions in real time. So the difference there is you're very limited in this tool to going against the data that is in the database. What we're building is solutions where you're not limited to the data in the database, where you can do these batch predictions. Here you saw Todd talk about one prediction at a time on one chemical from the predictions interface. We already have a proof of concept tool if you want to drop 100 smile strings in for chemicals that we do not have. Those predictions will happen in real time. So we're always moving that ahead, and that will be available publicly. So the summary of what you've seen really is this growing capability around providing this central hub to data, various types of data coming together, experimental data, predicted data, hazard data, exposure data, etc. These multiple types of searches that we have here, we know we're not done. We know we have more to do, but we also have limited, don't have a limited scope. We have limited resources. So I'm sure you can understand that some of these take real time to deal with. These proof of concepts that we build, we do the research effort independently of the production software team. We try and develop the best approaches, the best ways to visualize the data, the best ways to bring the data together. And then we work with the software team later to rebuild it into more of a production level architecture. And then again, the downloadable files you saw, hopefully you'll think of as valuable, comma separated, tab separated, and Excel files. And of course, that additional formats that many of you might not care about, but certainly we have a lot of users in the world who do. This SD file, this structure file where you can download 1,000 chemical structures laid out, represented as the appropriate structure depictions. That's how we deal with chemicals in the Chem Informatics world, is in these SD files and mol files and smiles. So coming soon, I don't know if you'll be blocked, if you can see the top of the panel for Zoom, but it might be in the way for you. But it's coming soon is this Computational dashboard. This is a rebuild, total new architecture. It has lots of advantages to you. If you are already a user, you're going to find some distinct advantages over what you've been used to. So brand new, built from the ground up. Even the data handling, how we manage those data has been changed dramatically. So historically, the dashboard has been hitting a number of databases and bringing the data together, integrating it, and then delivering it out to you. But in this case, we've taken a data hub approach where all of the data are extracted and loaded from multiple databases into one central data hub. From that, we pull out a subset of that content to support the application in question, and that's called a data mart. The entirety of the data mapped together is called the data hub. snap of data to support the application is called the data mart. And as we bring up different applications for different purposes, we grab different subsets of data from that data hub. If you've been using the dashboard for a while, and I hope we have not only new users on the call, you will have noticed that with every release, we've released somewhere between 10 and 20K, generally 20K with each release. This one will be no difference. The one that goes out in November will be an additional 20,000 chemicals. But in 2022, as I explained earlier on, CAS, Chemical Abstract Service, were kind enough to enter into a community-based agreement to serve us all. They released 500,000 chemicals. And it's on a website called commonchemistry.org, if you haven't seen it. That's as a result of years of discussions with UPAC, International Union Pure and Applied Chemistry. I've been part of those for many, many years. The initial version of Common Chemistry was 7,000 chemicals. Now we've hit, 8,000 chemicals. We're now at 500,000 chemicals. And by bringing in that open data into the system, we've taken an enormous jump, 300,000 chemicals. And this has dealt with a lot of the complexities around UVCB chemicals that we've had to deal with. Lots of polymers, no structures for us to predict on, but lots of polymers and Qscr inventory chemicals that we need to support, et cetera, et cetera. Now what we will be doing with those chemicals, we'll be mapping these UVCB chemicals to single members of the mixed formulations. For example, monomers, complex polymers will be mapped to monomers. We will take on all of that work as part of our effort for curation. Most of the lists that are already available to you publicly will have been updated and grown. So as new inventories get released, we grab that inventory, we curate it and map it. We're in the process of completing the August release of the Qscr inventory right now. We're always behind the 8 ball. We're always chasing new lists coming available, but we're over 310 lists already on the public dashboard. That same list will be going out with the new version, plus some additional ones. And internally, we have over 800 lists. Some of those serve individual projects. Internally, they don't go public. But eventually, our intention is to keep pushing out new lists of interest. And I put some of those in the chat box for you. So terpenes in vape, for example, I have 19-year-old twins. They both vape. I wish they didn't, but they do. So I try to highlight some of the toxicity of chemicals for them in that. But it actually was good timing flying out to the West Coast, out to Region 10. They were interested in terpenes in vape. So we build these lists. Tire chemicals in tire chrome rubber, chemicals in hydraulic fracturing, storage tanks. These lists continue to update. So just in the past 4 weeks, we put in the 4 separate categories of IARC, 1, 2A, 2B, and 3. Those are now separate lists. If there are any lists missing, if there are any lists you think we should have focus some efforts on, and these are easy for us to assemble, pull together, then we can add that to our curation backlog. The ToxFile database that has been built by Richard Judson, that's the hazard data. That's been expanded with tens of thousands of new data points. There are additional chemicals, a very sincere effort by the team to pull together a lot of PFAS chemical data, including property data. Todd has led a charge to pull together property data for PFAS. Those will go out in the future. The models will be rebuilt using PFAS data. But ToxFile itself is going to have an awful lot of data for PFAS-related chemicals. There are new table handle capabilities across the entire application that make it easier for you to switch on and off columns, to reorder, to sort. We had some heterogeneity across the application previously. Different tables would work different ways. We've standardized on a specific table handling. And if you know how to use it in one place on the application, you can use it in all. And then the batch search performance, we were limited historically to less than 5,000 identifiers, and it could take 30, 40 seconds for a couple of thousand chemicals, up to minutes for 5,000 chemicals. Now it can be just a few seconds, 5 to 10 seconds to deal with 5,000 to 10,000 chemicals. So batch search performance has been massively enhanced. We hope you enjoy that. You've heard from Todd He's been a pleasure to work with on this application. Hazard comparison dashboard is what you're seeing here. This is the, as Meg will call it, maybe the Christmas gift, the colored lights that will shine up based on toxicity. But there are actually multiple modules to this dashboard. The entire application is called the hazard comparison dashboard. This particular view is the hazard module. But if you look across the top here, let me bring up my pointer. This is hazard, so this is the hazard module. Predict module is the ability to submit 100, 1,000 chemicals and predict test predictions, toxicity estimation software predictions in real time. Now, real time, it may take a few minutes to go through and generate all of those predictions, but it also shows all of the prediction reports. So that's batch prediction. Search here, this is structure, substructure, similarity searching. It also will allow you to display those chemicals with a particular substructure that have toxicity data available in the hazard comparison dashboard. Standardization, this is a tool that will mostly serve modelers ultimately for producing the Qscr ready chemicals that people will build predictions around or push through predictions. And you heard me talk a little bit about MS ready, Qscr ready. This is where we collapse chemicals into certain forms in order to know what you can detect by mass spectrometry. And that's a standardization module that we believe will serve the community once it's rolled out publicly. It gives us a lot of control over the rules that we have, and it's in testing right now for ourselves. Toxprints, this is research work conducted by our colleague Anne Richard. Many of you may know of the work that collectively went on between FDA and EPA for something called the Toxprint chemotypes. And there is a tool for the chemotype. These are specific substructural search elements that are very useful as descriptors for modeling. And this is work that Anne has been conducting for the past few years. This will also be made available. And right now we're working on an alerts module for ASHB alerts and threshold of toxicological concern alerts. Brand new, literally come up in the past 3 weeks, and is yet another proof of concept module that we are building. So this will ultimately be going public. As I said, we are in the process of working with a team to deploy this publicly. We'll then need to scan it for security vulnerabilities and make it available. We will make sure to return to this group and make the announcement when it's ready so that you're all aware of it. If you wish to get hold of some of the materials that we have presented over the years, so Todd, Catherine, myself, our colleagues, Richard Judson and Richard, there's so many of us that are out there. Certainly pre-COVID, we were out on the road and conferences giving talks, and now all we do is stand in front of Zoom meetings and Teams, of course. It's good to engage with you like this, but this may not be enough. So you may need more information. You might want to dive into specific aspects of the dashboard. So there are lots of presentations available. I tend to point to ones that I know where they are. So these links will lead you into things like SlideShare presentations, or you can go to the EPA Figshare and search on my name, Todd's name, Catherine's name. I will show you where that is shortly. We have some communities of practice videos. That's about 2 hours, module by module of the dashboard, kind of like category. So you want to focus a section on bioactivity. That'll be 25 minutes. Exposure, that'll be 25 minutes. So you can watch these in snippets, kind of like watching a Netflix series. The manual will take you to a very succinct manual that will give you enough about how to learn how to use the dashboard. And Todd has a wonderful manual up there, much more details about how test was built, how the models were built, etc. And streaming on the homepage all the time is new information. So if you just follow the page, you will see that we're announcing new publications, training sessions, etc., etc. I do want to highlight where we have data available. So if you choose to download the data, you can get to it. Just try to figure out how to move this thing. All right, so on the downloads right here, can you confirm you can still see the page?
Yes, we can.
Okay, great. So this is the downloads page. So again, we're on the public dashboard here. This is the downloads page. You can find files that we have provide access to the SDF file. That's all of our chemicals as a file that you can download. We have predicted property data. These are commonly out of date relative to what's available because it can take a long time to produce each of these and make them available, but it's a good starting point for you to access the data. So watch the data page, but I do want to show you where we version everything. So if you go to EPA Figshare right here, epa.figshare.com, you can go on here and search for Todd, for example, and you will find 115 results for Todd. Actually, that's Matt Martin. So that's Todd Martin's presentations. This is Gabriel Sinclair, who works on the team to pull together data and building models, et cetera, et cetera. So there's lots of things here, and you want to look at the posters, apply the filters. You will get subsets of that. These are presentations that have been given over the years at different conferences. You can also get directly to just data sets. So for example, if you want to find, in vitro data,
And while you're searching around, Anthony, A4 will be creating a resources sheet along with the short course recording that'll include all of these resources so that we don't miss a single thing. And then while I have you, do you have any presentations or posters planned for the March 2022 SOT meeting in San Diego for those of us who belong to SOT and who will be going to a live meeting finally?
Let's hope it's a live meeting.
Right. Fingers crossed, right.
Yeah, I've been heading to 5 live meetings and never made it yet.
Right, seriously.
Yes, there will, the intention is to be at the SOT meeting. There will be abstracts submitted. They're not in yet. I think they've got a December deadline. That also will be at the ACS meeting. Todd and I will be there. The intention would be to cover the latest and greatest release of the dashboard, some of our modeling progress, et cetera, et cetera. And generally, EPA does have a booth, assuming that with COVID things operate the same. We'd love to spend some time with you in front of the computer and answer your questions directly, et cetera. So this is EPA Figshare. I'm looking at the data sets. This is in vitro DB. You will be able to download the files like this. We try to update these as soon as we've done a release so that you can get to the latest and greatest data, and then we link them back to the dashboard. So that's about it before we start a live, 10, 15 minutes of answering questions with real chemicals. I don't know if Todd and Catherine have any additional comments to make about their future work. Nope. Okay.
Todd, sorry, I was trying to get off mute, but my thing was stuck. Well, my main future work is to be able to add new Qscr models. So we be able to on the fly add and remove models as we see fit and build them with a variety of different Qscr methods, and then just to be able to deploy to more easily deploy new models into our tools. So that's one of our main things. And then just being able to recurate the models themselves and update and add more data. There's lots of new data being made available. So, we could, theoretically build a water solubility model based on twice as many chemicals, add more hazard and more tox endpoints, and just be able to have a system that automates all that. So it makes it easier to roll out new models. So that's my main focus right now. So.
Catherine, anything you want to cover?
Yeah, sorry, I thought I having trouble with the mute again. I think I covered most of it in talk, but I'll just go ahead and reiterate it. We're working on making our factotum application publicly available so that people can look through our exposure data. So hopefully that will be out in the near future. Rebuilding those Qscr models, and then also another database we're trying to incorporate in would be a multimedia database where we have information on chemicals and the different media they would have been identified in. So whether that's groundwater, surface water, soil, breast milk, stuff like that. So that's the sort of exposure flavor information that you can look forward to in the future.
Thank you, Catherine. So I'm putting this bookend back up. This might be a good one for this particular audience to look at, but during the session, we're putting links into multiple publications from Todd, from Catherine, from our colleagues that may be of interest to you, but feel free to follow up with us. We've been the ones that have taken the chance to talk with you today. Hopefully you've enjoyed it. We've got a few minutes left, but I just want to make sure that you understand that we're sitting on the shoulders of so many brilliant people that came before us. Todd's been here a lot longer than me. I've been here a little bit longer than Catherine, and before us all came the people who really set up NCCT, and we're surrounded by very, very clever people working hard every day to make this happen. We welcome any of your feedback and follow up after the session. Your questions that come from using this help enrich it in the future, because we consider what you're asking for and what we're missing. And we also acknowledge the myriad of groups, websites, open source developers who've delivered aspects of the tools and data that we use underneath this dashboard. We definitely couldn't have done it without everybody else's contribution across the community. So if you have any questions, I can switch to the dashboard and we can continue to work on that for the next few minutes if there's any interest. Otherwise, we can give everybody a little more time to have a cup of tea, in my world at least.
So members of the audience, feel free to raise your hands or enter questions or comments in the chat. Molly's monitoring that. I did have a couple questions. For many of us who do a lot of work in the cleaning products industry, microorganisms and enzymes are powerhouses, and they're obviously made of chemical substances as well. So everyone's always looking for the next best thing in a microorganism or an enzyme. Are you going to be adding biological substances and proteins and enzymes more and more to the CompTox chemicals dashboard as well, in addition to neat chemical substances? Is that something that's been discussed or tossed around at all?
We've made decisions to this point that has allowed us to exclude a lot of the complexity around trying to manage various strains of things like proteins, organisms, etc. So a lot of that is very hard to distinguish in our world. CAS do it with a CAS number, and when they release their common chemistry website, I highlighted a few hundred chemicals that in our world were exactly the same, and actually in their world were exactly the same, except for the difference in CAS numbers and a slight change in annotation. That said, in the Qscr inventory, we do have to deal with an increasing amount of complexity about how to map information together. So I would expect over the next few years, you will see some efforts in that. In terms of relationships with enzyme-based databases, we will provide links from chemicals into things like Brenda, which is one of the primary enzyme databases out there. So chemicals that are in Brenda related to enzymes, we will have that mapping in place from the external link system.
Awesome.
There's a question around nanomaterials. So one of the things that we did around nanomaterials is we worked on something called the EPA nanobase. Assuming you can still see my screen. This is the EPA nanobase. You can find information about this online. This was originally led up by a gentleman called Will Boys, who was looking into the toxicity of nanomaterials with one of our colleagues called Paul Martin. You can find details on here, publications, etc. And what we did with Nanobase is we tried to deal with the complexities. This is an example of where things can be challenging of managing nanobase data. None of the nanomaterials themselves have distinct structures. That's why you see here this non-structured data set. Let me show you. So they're all annotations that say things such as, if I go to a chemical that has a related structure, i.e. that one absorbs the surface. So we have nanosilver, sodium citrate, 2.6 nanometers. This is the description. Maybe you can't see it. Let me zoom in a little further. From the description, which is hosted inside the database and is generated from the people building the database, we're able to create this name, this identifier based on the description. We do have a slight error here, this 2,6, but let me show you maybe in the new database that we're building, CCTE. We do manage the nanobase data here. Let's see. Okay, so this name means it's a silver core coated with sodium citrate at 2.6 nanometers particle size. And the material is obtained from an unreported source. So this is our attempt to try and come up with an identifier that describes the nanomaterial at least. Notice it doesn't have a CAS number. Not every chemical in the dashboard has to have a CAS, but it does have a unique substance identifier. We are working with the eNanoMapper group in Europe. That's one of my colleagues called Holly Martinson. She's heading up the database development now that Will has left. She's working with Paul Martin. So this, you will see more expansion here. And the intention would be to link from things like the citrate coating. We'll be able to find every single nanoparticle which has a specific coating, like polyvinyl, pyrrolidone, citrate, et cetera, et cetera. So we will have some level of Chem Informatics bringing these data together. But there are other people in the world, certainly in Europe, leading up nano material databases. Let's see any other questions right now. Any other questions?
And I'm not seeing any hands up either, Tony.
Okay.
Okay, let's bring it on home then.
Yep, I know it's been a long ride with us, so I will let you close it down. And thank you for giving us the opportunity to talk about our work. It's greatly appreciated.
Great, wonderful. All right, thank you everyone for sticking with us during this day. So much information. Molly, do you want to forward the slides?
Yeah, Tony, if you could stop sharing, I have just a few slides to end on.
Sure.
Great.
Great. So obviously we've learned a lot today. Everyone was listening, and I could tell no one was checking their emails or texting. If you do need a certificate of attendance, particularly for those of us with ERTs or DABTs, please reach out to Molly Jacobs. We're happy to provide you an A4 CE credit and to document your attendance today. And remember, recording of this short course will be available next week on the A4 website, www.saferalternatives.org. But we're not done yet. We're just about to start this week, the A4 Symposium. And for those of you who haven't registered yet, there's still time. Please go to the saferalternatives.org website. Tomorrow's session is going to be great. It's with Joe Rodricks, one of my former bosses, one of the best risk assessors in the world and toxicologists, Bill McDonough, the founder of Cradle to Cradle Thinking, and John Warner, who created the concept of green chemistry. Well, you have to ask Bill. Bill might say he did, but it'll be a great session. It's one of 7 coming up this week. We need you to be part of A4. We hope you attend. There's a lot of learning left to do and so much work for all of us to do to get to safer and sustainable. So I hope to see you at the symposium. Finally, as I said, join the A4, be part of our movement, to share and teach each other. So we hope to see you next week. Thank you again, or tomorrow. Thank you again, Tony, Catherine. It's been really great, informative, and we'll post the recordings next week. Thank you.